From the mysterious depths of dark matter to the dazzling worlds of distant exoplanets, from the fiery birth of the cosmos in the Big Bang to the enigmatic pull of black holes, our universe is a vast arena filled with phenomena that continually stretch the boundaries of human understanding. In this documentary, we embark on a journey through space and time to unravel the most captivating mysteries that challenge the very core of modern physics. By exploring the latest scientific theories alongside groundbreaking observations from cutting-edge telescopes and space missions, we invite you to join us as we unlock the secrets woven into the fabric of the cosmos. When we speak of the observable universe, we refer to the immense region of space that lies within our cosmic horizon, the limit of what we can see or detect from Earth. This region extends roughly 13.8 billion light-years in every direction, a staggering distance that highlights the immense scale of our universe. Within this expanse lie billions of galaxies, each a bustling metropolis of stars numbering in the millions or even billions. These galaxies harbor countless planets, some of which may resemble our own blue world, while others exist under conditions that challenge our imagination. Yet, this observable portion of the universe comes with a fundamental boundary, the speed of light. Since light travels at a finite speed, about 300,000 kilometers per second, it takes time for light emitted by distant objects to reach us. Objects beyond this horizon remain hidden from our view because their light simply has not had enough time to traverse the cosmic distances since the universe's beginning. This means that the observable universe is not the totality of existence, but merely the portion accessible to our instruments and senses. What makes the observable universe truly awe-inspiring is that it is not just a static snapshot of distant stars and galaxies, but a dynamic archive of cosmic history. As we gaze deeper into space, we are also looking back in time. The light arriving from remote galaxies has traveled for billions of years, carrying with it the story of their formation and evolution long before humans ever walked the Earth. Each photon that reaches our telescopes is a messenger from the past, offering a glimpse of a cosmos in constant flux. Beyond the limits of this observable frontier lies the entirety of the universe, a vast, possibly infinite expanse that encompasses all of space, time, matter, and energy. This uncharted territory may hold countless more galaxies, stars, and planets forever beyond our reach, because the light from these regions has either not arrived or has been stretched so much by the expansion of space that it shifts beyond the range of our detection instruments. The phenomenon known as redshift causes the light from these fast-receding objects to move into longer invisible wavelengths, rendering them effectively invisible to us. The true size and shape of the universe remain among the greatest enigmas in cosmology. Scientists continue to debate whether the cosmos is finite, like the surface of a sphere, or infinite, extending endlessly beyond our wildest imagination. As research advances with new technologies and theoretical breakthroughs, humanity inches closer to understanding the grand scale and ultimate fate of everything we call the universe. Join us as we continue this incredible journey of discovery, where each revelation opens the door to deeper questions and greater wonders. Additionally, while we have a clearly defined boundary marking the edge of the observable universe, the reality beyond this boundary may be far more vast, potentially stretching on infinitely beyond anything we can currently grasp. This idea fundamentally challenges our understanding of the cosmos, pushing scientists to explore new theories about the universe's overall shape, curvature, and hidden structure. At the same time, they are wrestling with the enigmatic nature of dark matter and dark energy, mysterious substances that together make up about 95% of the total mass and energy of the universe, yet remain largely invisible and undetectable through conventional means. Measuring the size of the observable universe depends on a blend of careful observation, the physics of light travel, and foundational principles from cosmology. The process begins with something familiar yet profound: the speed of light. Light travels at a constant speed in a vacuum, about 186,000 miles per second, or roughly 300,000 kilometers per second. To put this in perspective, sunlight takes around 8 minutes to journey from the surface of the sun to Earth. When astronomers peer into the depths of space, they are not simply looking at distant points of light. they are looking back in time. The light arriving from distant galaxies has traveled for billions of years to reach us, effectively acting as a cosmic time capsule, revealing how those galaxies appeared in the ancient past. To determine how far away these celestial objects lie, astronomers use a range of sophisticated techniques. One such method is called parallax, which involves observing a nearby star from two different positions in Earth's orbit around the Sun. By measuring the apparent shift in the star's position against the background of more distant stars, astronomers can calculate its distance from us, anchoring our understanding of cosmic scales. Another approach involves so-called standard candles, such as certain types of supernovae or variable stars, which have predictable intrinsic brightness. By comparing how bright these objects appear from Earth, astronomers estimate how far away they must be. Then there's redshift, a critical tool that measures how much the wavelengths of light from distant galaxies have been stretched as those galaxies speed away from us due to the universe's expansion. The greater the redshift, the farther the galaxy. Combining these methods allows scientists to calculate the maximum observable distance, the furthest edges of what we can see in the universe. Since the universe has been expanding for roughly 13.8 billion years, the light from its most distant reaches has traveled for billions of years to arrive here. However, because space itself has been stretching over time, the furthest edges of the observable universe are currently estimated to be around 46 billion light-years away in every direction, much farther than the universe's age in years might suggest. This boundary defines the limits of what we can observe, but not necessarily the full extent of the universe itself. Our measurements and understanding are continuously evolving thanks to technological advances and improved observational tools. Instruments like the Hubble Space Telescope have transformed our view of the cosmos, revealing countless galaxies at staggering distances. Looking forward, next-generation telescopes such as the James Webb Space Telescope promise to deepen our cosmic insights, pushing the boundaries of observation further than ever before. As our ability to see the universe grows, so too does our awareness of its immensity and the tantalizing possibility of realms beyond our reach. Among the most distant objects we can detect are galaxies formed just after the Big Bang. For example, the galaxy known as GN-Z11 sits approximately 13.4 billion light-years away. This means the light we observe from GN-Z11 today left that galaxy when the universe was only about 600 million years old, offering a rare glimpse into the earliest era of galaxy formation, an epoch when the cosmos was cooling and expanding rapidly after its explosive beginning. Even more intriguing is the galaxy designated HD1, reported to exist roughly 13.5 billion light-years away. This discovery suggests HD1 may have emerged even earlier than GN-Z11, allowing astronomers to probe conditions in the universe's infancy and gain valuable clues about the dawn of cosmic structure and star formation. The light streaming from these remote galaxies provides critical information about how stars formed and evolved during the universe's first few hundred million years. In addition to distant galaxies, scientists also observe quasars, exceptionally bright and energetic objects powered by supermassive black holes at the centers of young galaxies. These quasar beacons shine across vast cosmic distances, acting as cosmic lighthouses and offering further insights into the early universe's energetic processes. Together, these distant galaxies and quasars compose a fascinating mosaic, revealing the grand story of cosmic evolution, from the universe's mysterious beginnings to the vast expanse we strive to understand today. One of the most distant known quasars, designated J001, lies approximately 13 billion light-years away from Earth. Remarkably, this quasar formed just 700 million years after the Big Bang, providing a stunning glimpse into the universe's infancy. Its existence reveals that even during these early cosmic epochs, galactic nuclei were extraordinarily active, showcasing the intense processes of galaxy formation taking place amid the chaos of a young universe. These remote, ancient objects challenge our deepest assumptions about cosmic evolution, offering a window into conditions that prevailed when the cosmos was still in its formative, turbulent stages. Quasars like J001 captivate astronomers because they serve as time capsules, preserving clues about the fundamental forces and dynamics that shaped the early universe. Each new discovery nudges humanity closer to unraveling the profound mysteries surrounding galaxy formation and the laws governing cosmic behavior. The quest to identify even more distant celestial bodies is ongoing, fueled by the desire to map the universe's timeline with ever greater precision, and to better understand how the vast cosmic structures we see today gradually emerged from primordial chaos. Our comprehension of the observable universe has evolved dramatically since ancient civilizations first gazed upward. Early cultures interpreted the night sky through myth and religion, assigning stories to constellations without grasping their scientific nature. The Renaissance ignited a revolutionary shift in this perspective. Visionary astronomers like Nicolaus Copernicus and Galileo Galilei challenged the long-held geocentric belief that Earth was the universe's center, and instead demonstrated that Earth revolves around the Sun, situated within an immense expanse dotted by countless stars. As telescopes grew more powerful, so too did humanity's understanding of the cosmos's vast structure and scale. The 18th and 19th centuries introduced trailblazing figures such as Edwin Hubble, whose meticulous observations transformed nebulae, previously thought to be clouds within our own galaxy, into distant galaxies in their own right. This revelation expanded the cosmic horizon dramatically. Hubble's work also showed that these galaxies are receding from us, a discovery that laid the foundation for the concept of an expanding universe. The insight of an expanding cosmos paved the way for the Big Bang theory, which fundamentally reshaped scientific thought about the universe's origins and evolution. In the decades that followed, the discovery of the cosmic microwave background radiation, often abbreviated as the CMB, provided compelling empirical evidence supporting this theory. The CMB represents the faint afterglow of the Big Bang, a relic thermal radiation left over from a time when the universe was still young, hot, and dense. Detected uniformly across the entire sky, the CMB offers a snapshot of the universe approximately 390,000 years after the Big Bang, during a phase called recombination. This was a pivotal moment when protons and electrons combined to form neutral hydrogen atoms. Prior to recombination, the universe was opaque because free electrons scattered photons, preventing light from traveling freely. But after this phase, the universe became transparent, allowing photons, the particles of light, to move unhindered through space. The CMB is this very light, still observable today, carrying invaluable information about the early cosmos. Technological advancements in recent decades, including space-based observatories and sophisticated detection techniques, have further enhanced our ability to study distant galaxies and cosmic phenomena. These innovations have led to breakthroughs in measuring the rate at which the universe expands and deepening our understanding of elusive components like dark matter and dark energy. Together, these mysterious substances constitute the majority of the universe's mass energy content, yet their true nature remains one of the most profound puzzles in modern cosmology. As our observational tools continue to improve, missions like the James Webb Space Telescope are poised to push the frontiers of our knowledge even further. By peering deeper into space and further back in time, these instruments aim to shed light on the earliest formation of galaxies, stars, and planetary systems. Each new exploration enriches our appreciation for the universe's incredible complexity and vastness, inviting scientists and curious minds alike to ponder the cosmic mysteries that surround us and to reflect on our place within this grand celestial tapestry. By analyzing the subtle fluctuations and tiny temperature variations in the cosmic microwave background, or CMB, scientists unlock a wealth of information about the universe's fundamental nature, its structure, composition, and how it has evolved over billions of years. These minute irregularities in the CMB reveal early variations in density, the seeds from which galaxies, clusters, and the vast cosmic web emerged. Over time, these density differences grew, shaping the grand architecture of the cosmos. The data extracted from the CMB also allows researchers to precisely measure essential cosmological parameters. These include the age of the universe, estimated to be about 13.8 billion years, and the proportions of its various components: ordinary matter, mysterious dark matter, and the enigmatic dark energy driving accelerated expansion. This ancient radiation serves as a cosmic blueprint, offering a foundational baseline for understanding the universe's large-scale properties. Space missions such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have played pivotal roles in capturing high-resolution maps of the CMB. Their measurements have enabled scientists to refine and enhance cosmological models, improving our grasp of profound questions about the universe's shape, its rate of expansion, and the underlying physics governing cosmic evolution. As one of the pillars of modern cosmology, the CMB remains a vibrant area of research, continually opening new avenues to unravel the mysteries of our universe's origins. Several robust lines of evidence converge to support the Big Bang theory, the leading explanation for how the universe began and transformed over time. Among the most compelling proofs is the very existence of the cosmic microwave background radiation. This faint, uniform glow of radiation permeates the entire sky, acting as a snapshot from roughly 390,000 years after the Big Bang. Its discovery perfectly matches predictions made by the Big Bang model, confirming that the universe expanded from an extremely hot, dense state, cooling gradually until this relic radiation could finally travel freely through space. Another cornerstone of evidence comes from the observed redshift of distant galaxies. Edwin Hubble's groundbreaking discovery showed that galaxies are moving away from us, and the farther they are, the faster they seem to recede. This observation, now known as Hubble's law, directly implies that the universe is expanding. If everything is moving apart today, then logically, the universe must have originated from a much smaller, hotter, and denser point, a concept at the heart of the Big Bang framework. The Big Bang theory also predicts the primordial creation of light elements during the universe's earliest moments through a process called Big Bang Nucleosynthesis. This synthesis produced helium, deuterium, lithium, and other light nuclei in specific proportions. Observations of their abundances in the cosmos align strikingly well with these predictions, providing further evidence that these elements were forged in the extreme conditions of the young universe. Moreover, the large-scale distribution of galaxies and clusters across the cosmic landscape supports this picture. The way these structures are spread and clumped can be traced back to the growth of tiny initial density fluctuations seeded in the primordial universe and magnified as it expanded and cooled. Advanced computer simulations based on the Big Bang model accurately reproduce these cosmic patterns, strengthening the theory's validity. Together, these diverse lines of evidence form a coherent narrative of cosmic evolution, establishing the Big Bang theory as the prevailing explanation for the universe's origin. In the first fleeting moments after the Big Bang, the universe underwent staggering transformations. This earliest epoch, often called the Planck epoch, lasted for an unimaginably brief time, around 10 to the power of negative 43 seconds. During this period, temperatures soared beyond comprehension, hotter than anything we could ever recreate, and the universe was filled with a chaotic, dense soup of fundamental particles like quarks, electrons, and neutrinos, all in a state of energetic equilibrium. As the universe rapidly expanded and cooled, significant changes unfolded. Within the first 100 seconds, quarks began combining into protons and neutrons, a process known as baryogenesis. These particles then entered a phase of nucleosynthesis, during which they fused into heavier atomic nuclei. Helium emerged as the most abundant product, accompanied by trace amounts of deuterium and lithium. This elemental synthesis laid the foundational chemical makeup for all matter in the cosmos. By the time about 390,000 years had passed, the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, marking an event called recombination. This critical transition transformed the universe from an opaque, hot plasma into a transparent expanse, allowing photons, particles of light, to travel freely for the first time. The release of these photons is what we detect today as the cosmic microwave background radiation, a relic echo from this formative era. The dynamics governing the young universe were ruled by fundamental forces, among which gravity began to dominate as expansion progressed. Gravity's pull orchestrated the gradual gathering of matter, leading eventually to the formation of the vast cosmic structures, galaxies, clusters, and superclusters that fill our universe today. The study of these processes continues to deepen our understanding of where we come from and how the cosmos continues to evolve. The very beginnings of the cosmos hold the key to understanding how everything we see today, galaxies, stars, planets, and ultimately life, came to be. Long before the dazzling tapestry of galaxies stretched across the night sky, the seeds of these immense structures were sown in the subtle irregularities present in the earliest moments of the universe. These tiny density fluctuations, barely perceptible, set in motion a cosmic dance of matter and energy that would unfold over billions of years, crafting the complexity of the universe as we know it. Right after the Big Bang, an extraordinary phase known as cosmic inflation transformed the universe in the blink of an eye. This was no ordinary expansion. It was an explosive growth spurt so rapid that the universe's size increased by at least 100 trillion times in less than a trillionth of a second, specifically between 10 to the minus 35 and 10 to the minus 32nd seconds after the Big Bang. This mind-boggling expansion stretched space itself, smoothing out any wrinkles and irregularities in the fabric of the cosmos. One of the most profound mysteries this rapid inflation helps solve is why the universe appears so uniform, no matter where we look. When astronomers scan the cosmos, they observe the cosmic microwave background, the afterglow of the Big Bang, with an almost perfect consistency in temperature across the sky. Without inflation, regions of space separated by vast distances should have wildly different temperatures and properties, as they would have had no chance to interact or influence each other. Inflation reveals that these regions were once tightly packed together before being flung apart at incredible speeds, spreading and evening out any differences, creating the remarkable isotropy we see today. But cosmic inflation does far more than explain uniformity. The rapid expansion magnified tiny quantum fluctuations, minute random variations at the subatomic scale, into cosmic-sized ripples in the density of matter. These fluctuations became the blueprint for the universe's large-scale structure, acting as gravitational wells that drew matter together to form the first stars, galaxies, and clusters. In essence, inflation not only accounts for the smoothness of the universe, but also sets the stage for the intricate cosmic web that stretches across billions of light years. In addition, inflation predicts that the universe is flat on large scales, a fact confirmed by precise measurements of the cosmic microwave background and extensive surveys of galaxies. This geometric flatness means that the universe will continue expanding indefinitely, influenced by the distribution of matter and energy shaped during those earliest moments. As scientists delve deeper into the mysteries of inflation, they uncover vital clues about the fundamental forces and particles that govern the cosmos and the very nature of space and time. Following this explosive beginning, the universe entered another crucial phase, the formation of its first elements through a process called Big Bang Nucleosynthesis. In the first few minutes after the Big Bang, the universe was an incredibly hot, dense plasma, teeming with protons, neutrons, and electrons. As the universe expanded and cooled, conditions became just right for these particles to combine and form the nuclei of the simplest atoms. At this early stage, protons and neutrons themselves had recently formed from quarks, the smallest known building blocks of matter. Through nuclear fusion, these protons and neutrons began to merge, creating the first atomic nuclei. Within just a few minutes, about 25% of the universe's mass had fused into helium-4 nuclei, which contained 2 protons and 2 neutrons. Alongside helium, trace amounts of other light elements like deuterium, lithium, and beryllium were synthesized, each a testament to the precise conditions of temperature and density during this brief, fiery epoch. This delicate balance was short-lived. As the universe continued to cool, nuclear reactions ceased approximately 5 minutes after the Big Bang, halting the formation of new atomic nuclei. The result was a universe composed mainly of hydrogen, about 75%, and helium, with only small traces of these other light elements. These primordial building blocks laid the groundwork for everything that followed. Over the next billions of years, gravity gathered this primordial matter into vast clouds that ignited as stars. Within these stellar furnaces, hydrogen and helium fused into heavier elements like carbon, oxygen, and iron, a process called stellar nucleosynthesis. These elements, forged in the hearts of stars and scattered across space by supernova explosions, enriched the cosmos with the raw materials needed to form planets and ultimately life itself. From the quiet fluctuations in the early universe to the blazing crucibles of stars, the story of cosmic evolution is a breathtaking journey from simplicity to complexity, shaping the universe into the wondrous expanse we explore today. Ultimately, these primordial processes laid the foundation for the formation of planets and the very building blocks of life itself. The study of Big Bang Nucleosynthesis remains a cornerstone in our quest to understand the origins of the first elements and their profound significance within the cosmic timeline. This early phase of the universe's history reveals how the simplest atoms came into existence, setting the stage for all matter that followed. The cosmic web is an awe-inspiring, large-scale structure of the universe, sprawling across unimaginable distances like a colossal cosmic spider web. This intricate network is composed of interconnected filaments and vast bubbles formed by galaxies, clusters of galaxies, and the mysterious dark matter. Far from being randomly scattered, galaxies align along these complex strands, tracing the hidden scaffolding of the cosmos. Within this vast web, dense regions known as knots or clusters serve as hubs where hundreds or even thousands of galaxies congregate. These clusters are separated by enormous voids, immense cosmic expanses where very few galaxies dwell, creating a striking contrast of cosmic architecture. The cosmic web's formation began in the infancy of the universe, emerging from tiny quantum fluctuations during the rapid expansion known as inflation, shortly after the Big Bang. These minute irregularities in the primordial plasma served as seeds, eventually growing into the sprawling structures we observe today. As the universe expanded and cooled over billions of years, gravity began to weave its intricate dance. Slightly denser regions pulled in surrounding matter, causing clumps to grow larger and denser. This process gave rise to the first stars and galaxies, which, through their mutual gravitational attraction, merged and evolved into more complex formations. The hidden hand of dark matter, an invisible substance that does not interact with light or electromagnetic forces, played a crucial role in this cosmic ballet. Accounting for a significant fraction of the universe's total mass, dark matter shaped how ordinary matter coalesced into filaments, knots, and vast clusters, sculpting the large-scale structure of the cosmos. Galaxies, as they formed and matured, gathered gas and dust in their gravitational wells, creating fertile environments for the birth of new stars. Small groups of galaxies merged, gradually forming the colossal galaxy clusters observed today. These clusters, in turn, influenced their cosmic neighborhoods, pulling matter into an ever-growing dynamic network. The elaborate architecture of the cosmic web stands as a testament to the ceaseless processes of cosmic evolution, guided by gravity and the mysterious influence of dark matter. Modern astronomy employs a variety of sophisticated observational techniques, including massive galaxy surveys and advanced computer simulations, to probe the cosmic web in exquisite detail. These efforts continually deepen our understanding of this grand cosmic tapestry, unraveling the physical laws that govern the growth, distribution, and behavior of galaxies across the universe. The proposal of dark matter emerged from groundbreaking astrophysical discoveries that challenged our understanding of the cosmos. Astronomers observed a puzzling mismatch between the visible matter in galaxies and the gravitational forces acting upon them. One of the earliest clues came from the study of galaxy rotation curves. Scientists expected stars orbiting farther from a galaxy's center to slow down, much like planets in our solar system do as they orbit the sun. Instead, stars at the outskirts were found moving at unexpectedly high speeds, implying the presence of far more mass than what was visible in stars and gas. This invisible mass, now known as dark matter, exerts a powerful gravitational pull, holding galaxies together and influencing their dynamics. Additional evidence arose from observations of galaxy clusters, where the total mass inferred from the motions of individual galaxies far exceeded the mass of all visible matter combined. The gravitational binding of these clusters could only be explained by a substantial amount of unseen non-luminous matter, lending further weight to the dark matter hypothesis. Perhaps the most striking proof of dark matter's existence comes from gravitational lensing, where the gravity of massive galaxy clusters bends and distorts the light from more distant galaxies behind them. The degree of bending often surpasses what would be expected if only visible matter were present, revealing the significant influence of dark matter. Together, these lines of evidence have transformed dark matter from a theoretical concept to a fundamental component of our understanding of the universe, shaping everything from the smallest galaxies to the grandest cosmic structures. Additionally, measurements of the cosmic microwave background radiation, often abbreviated as the CMB, provided profound new evidence supporting the existence of dark matter. The CMB is essentially a faint glow of radiation left over from the Big Bang, acting as a snapshot of the universe during its infancy. By carefully studying the subtle patterns of temperature fluctuations within this ancient light, scientists gained a remarkable window into the universe's early composition. These tiny variations in temperature encode vital information about the total matter content spread throughout the cosmos at that time. When researchers analyzed this data, they discovered that the visible, ordinary matter, the stuff that makes up stars, planets, and people, could not possibly account for all the gravitational effects observed. Instead, the evidence pointed toward a substantial proportion of the universe's total mass energy being made up of something mysterious and invisible: dark matter. This unseen component appears to dominate the universe's mass budget and plays a critical role in shaping its structure. Together, these findings led scientists to a groundbreaking conclusion. Ordinary matter alone could not explain the gravitational behaviors seen in galaxies and galaxy clusters. Dark matter was proposed as an essential element, influencing not only the formation of cosmic structures, but also the ongoing dynamics of the universe's vast systems. Although its true nature remains one of the biggest puzzles in modern astrophysics, dark matter's gravitational fingerprints are unmistakable. Two key phenomena provide some of the most compelling observational evidence for dark matter: gravitational lensing and galaxy rotation curves. Gravitational lensing occurs when light from a distant celestial object, such as a faraway galaxy, passes near a massive object like a galaxy cluster on its journey toward Earth. The intense gravitational field of the massive cluster warps the fabric of space-time around it, bending the path of the light in a way similar to how a glass lens bends and focuses rays of light. This bending effect can produce spectacular visual outcomes, such as multiple images of the same distant galaxy, distorted shapes of background galaxies, or even perfectly circular arcs known as Einstein rings. When astronomers measure the amount of bending caused by gravitational lensing, they often find that the observed deflection of light is far greater than what the visible matter in the intervening cluster could produce. This discrepancy strongly suggests the presence of a large amount of unseen mass, dark matter, that adds to the gravitational pull and influences how the light travels through space. Complementing this evidence are galaxy rotation curves, which offer another crucial clue. By tracking the rotational speeds of stars at varying distances from the centers of galaxies, scientists expected to see a decline in speed as stars moved farther out. Much like planets in our solar system, orbit slower the farther they are from the sun. However, the observations tell a different story. Stars far from galactic centers orbit at unexpectedly high velocities, maintaining nearly constant speeds instead of slowing down. This flat rotation curve defies expectations based solely on visible matter. The stars, gas, and dust observed in galaxies simply cannot generate enough gravitational force to keep these outer stars moving so rapidly without flying away. The logical conclusion is that an extensive, invisible halo of dark matter envelops galaxies, providing the additional gravitational pull necessary to hold these fast-moving stars in orbit. Taken together, gravitational lensing and galaxy rotation curves paint a consistent and compelling portrait of a universe dominated by dark matter. Gravitational lensing reveals the hidden mass lurking within galaxy clusters, while galaxy rotation curves expose the vast, unseen halos surrounding individual galaxies. These observations not only confirm dark matter's existence, but also challenge and expand our understanding of the universe's fundamental makeup, sparking ongoing research to unravel its mysterious properties and interactions. Scientists have proposed several theoretical candidates for the particles that might make up dark matter, each rooted in advanced physics beyond the familiar particles in the Standard Model. The leading contenders include weakly interacting massive particles, or WIMPs. These hypothetical particles would have masses ranging from a few billion electron volts to several hundred billion electron volts, and would interact primarily through the weak nuclear force and gravity. Because they barely interact with ordinary matter, WIMPs are incredibly difficult to detect, yet they remain one of the most plausible dark matter candidates. Theoretical frameworks such as supersymmetry, an extension of the Standard Model, predict the existence of WIMPs. Supersymmetry introduces partner particles for all known particles, and the lightest supersymmetric particle is a prime candidate for dark matter. Its properties would perfectly align with the invisible, gravitationally influential nature of dark matter inferred from observations. Another fascinating possibility is the axion, an extremely lightweight hypothetical particle proposed to solve a deep problem in quantum chromodynamics, known as the strong CP problem. Axions would interact very weakly with ordinary matter and carry minuscule masses, making them elusive yet promising candidates for dark matter. Researchers are actively searching for axions by looking for their subtle effects, such as tiny electric fields generated when axions interact with strong magnetic fields in laboratory experiments. Sterile neutrinos also stand out as intriguing candidates. Unlike ordinary neutrinos, which participate in the weak nuclear force, sterile neutrinos would not interact via any of the Standard Model forces except gravity. They could have been produced in the early universe, and might explain some discrepancies in galaxy formation and large-scale cosmic structure. Their unique qualities could allow sterile neutrinos to account for both warm and cold dark matter scenarios, providing a versatile framework for understanding dark matter's role. In summary, while dark matter remains invisible and mysterious, its gravitational fingerprints are etched across the cosmos, from the bending of light by massive galaxy clusters to the unexpectedly fast rotations of distant stars. As scientists continue their quest to identify the particles behind dark matter, each new discovery brings us closer to understanding the hidden scaffolding that shapes the universe itself. Finally, primordial black holes emerge as one of the most captivating enigmas in modern cosmology. Unlike the more familiar black holes that form from the collapse of massive stars, these primordial black holes are thought to have originated in the infancy of the universe itself. In the chaotic moments following the Big Bang, tiny ripples in the density of matter could have been so extreme that certain regions collapsed under their own gravity, creating black holes without the need for stars. The masses of these primordial objects might span an extraordinary range, from the size of small asteroids all the way to several times the mass of our Sun. If these black holes truly exist, they could play a crucial role in one of the greatest puzzles facing scientists today: the nature of dark matter. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to current detection methods. Yet, its gravitational influence is undeniable, shaping the structure of galaxies and the universe on large scales. Primordial black holes present a fascinating candidate for matter because, unlike exotic particles, they are composed of ordinary matter compressed into ultra-dense regions. Researchers around the globe are dedicated to detecting these elusive objects through innovative experiments and astronomical observations, hoping to unravel whether primordial black holes could indeed account for a significant fraction of the universe's unseen mass. The search involves careful analysis of gravitational lensing events, where the gravity of a compact object bends light from distant stars, as well as studies of gravitational waves produced by black hole mergers. Turning now to another cosmic mystery, dark energy stands as a profound and perplexing force shaping the destiny of the cosmos. While dark matter pulls galaxies together through its gravitational attraction, dark energy pushes the universe apart. It is the driving force behind the accelerated expansion of space, a discovery that revolutionized our understanding of cosmology. Today, scientists estimate that dark energy makes up about 70% of the total energy content of the universe, dominating over all other forms of matter and energy combined. The story of dark energy begins in the late 20th century, during the mid-1990s, when two independent teams of astronomers set out to measure the rate of the universe's expansion using a remarkable cosmic tool, type Ia supernovae. These supernovae, exploding stars with nearly uniform brightness, serve as standard candles for gauging cosmic distances. Expecting to see the universe's expansion slow down due to gravity's pull, the teams were stunned to find the opposite. The distant supernovae appeared dimmer than anticipated, implying they were farther away than expected if the expansion were decelerating. This surprising dimness indicated that the universe was not just expanding, but accelerating in its expansion. This groundbreaking revelation led to the hypothesis of an unseen energy permeating all of space, counteracting gravity on the largest scales, a force now known as dark energy. One of the key insights into dark energy comes from its equation of state, which links its density to pressure, revealing that it exerts a negative pressure. This negative pressure acts like a cosmic repellent, pushing galaxies apart faster and faster, defying the attractive force of gravity. Scientists have proposed several theoretical frameworks to explain dark energy. Among these are the cosmological constant, a term originally introduced by Albert Einstein, quintessence, which suggests dark energy could be a dynamic field changing over time, and modifications to Einstein's general theory of relativity itself. Yet, despite decades of research, the true nature of dark energy remains one of the greatest unsolved mysteries in physics. Further evidence supporting dark energy's existence has come from a variety of observational probes. Measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, along with detailed maps of galaxy clustering, consistently reinforce the presence of this enigmatic force. These observations not only confirm that dark energy shapes the large-scale structure of the universe, but also guide scientists in refining their models of cosmic evolution. In sum, the universe is a vast and dynamic arena where unseen forces, primordial black holes, and dark energy challenge our deepest understanding. Each discovery peels back another layer of the cosmic veil, inviting humanity to explore the fundamental questions of our existence and the ultimate fate of all that we see in the night sky. The study of dark energy stands as one of the most profound and puzzling quests in modern cosmology. Unlocking its secrets promises to reshape our understanding of the universe's destiny and the very laws that govern cosmic expansion. This elusive force, discovered through careful observation of distant exploding stars called supernovae, has revolutionized our grasp of the cosmos. Dark energy now accounts for nearly 70% of the universe's total energy, an astonishing majority that shapes the grand cosmic landscape. While gravity is well known for its role in pulling matter together, forming stars, planets, and galaxies, dark energy operates in stark contrast. It acts like a mysterious pressure that pushes galaxies away from each other, causing the universe to expand at an ever-accelerating pace. This expansion is not just a gentle drift. It is an active, growing force stretching the very fabric of space-time. Imagine the universe as a vast, invisible balloon inflating continuously with galaxies carried along on its surface, moving further apart faster and faster as time flows on. What makes dark energy truly enigmatic is how it defies our conventional understanding of physics. Unlike any known form of matter or energy, it seems to be a property of space itself. The energy inherent in the vacuum of empty space could be driving this cosmic acceleration, or perhaps it is tied to gravity behaving differently over enormous distances. These competing theories illustrate just how little we fully comprehend this phenomenon. Scientists are left grappling with questions about the universe's ultimate fate. Will this expansion continue forever, isolating galaxies beyond a cosmic horizon so distant they become unreachable? Or will some yet undiscovered mechanism alter this course? Dark energy's uniformity on large scales adds to the mystery. It appears smooth and consistent across the cosmos, yet its origin and nature remain elusive. Ongoing research uses sophisticated telescopes and vast cosmic surveys to gather data, hoping to illuminate this dark force. Each discovery sharpens our picture of the cosmos and deepens the mystery of what the universe truly is and what it will become. Meanwhile, black holes represent another captivating frontier in our cosmic exploration. These are regions where gravity reigns with such intensity that nothing, not even light, can escape their pull. They form when massive stars exhaust their nuclear fuel. Without the outward pressure from fusion to counterbalance gravity, the star's core collapses, condensing into an incredibly dense object surrounded by an invisible boundary called the event horizon. Black holes come in different sizes. Stellar black holes form from stars roughly 20 times more massive than our Sun that end their lives in violent explosions known as supernovae. The star's outer layers are blasted into space, while the core implodes to become a black hole. At the other extreme lie supermassive black holes, giants residing at the centers of galaxies with masses millions or even billions of times that of the Sun. Scientists continue to debate how these colossal entities form, whether through the merging of smaller black holes or the collapse of enormous gas clouds. Between these extremes lies a mysterious class known as intermediate black holes, whose masses bridge the gap between stellar and supermassive. These objects are less common and harder to detect, and their origins are still subjects of active research. Despite their differences, all black holes share the defining feature of the event horizon, the point of no return beyond which everything, including light, disappears forever from the outside universe. The study of black holes pushes the boundaries of our knowledge about gravity and the nature of space and time. They force us to question fundamental physics, especially regarding information and how the universe preserves or loses it when matter crosses the event horizon. Each black hole discovery offers insights into stellar life cycles, extreme matter behavior, and perhaps even the fabric of reality itself. Together, the mysteries of dark energy and black holes challenge our deepest assumptions about the cosmos. As scientists probe these cosmic enigmas, we inch ever closer to understanding the universe's origins, structure, and ultimate fate, revealing not just the secrets of distant galaxies, but the profound laws that govern all existence. Some of the most profound mysteries in cosmology revolve around black holes, enigmatic objects that challenge our understanding of space, time, and gravity. Black holes are not all the same. They fall into distinct categories, each defined by their mass and how they come into existence. The primary types astronomers recognize are stellar black holes, supermassive black holes, and intermediate black holes. Each of these plays a unique role in the cosmic landscape, revealing different facets of the universe's evolution. Stellar black holes are the most common type. They form from the death throes of massive stars, stars that are typically more than 20 times the mass of our Sun. When these colossal stars exhaust their nuclear fuel, they can no longer resist the force of gravity. The star's outer layers explode outward in a brilliant supernova, while the core collapses inward, compressing into a singularity, a point of infinite density where gravity is so intense that nothing, not even light, can escape. These stellar black holes generally weigh in at a few to several dozen times the mass of our Sun, making them relatively small on the cosmic scale, but no less fascinating. On the opposite end of the scale lie the supermassive black holes. As their name suggests, these giants are extraordinarily massive, ranging from millions to billions of times the mass of our Sun. They lurk at the centers of most galaxies, including our own Milky Way, acting as gravitational anchors for billions of stars and vast clouds of gas and dust. How supermassive black holes form remains one of the greatest puzzles in astrophysics. Scientists theorize that they may grow from the gradual merging of smaller black holes or from the collapse of massive gas clouds during the early stages of the universe. Over billions of years, they accumulate mass by pulling in stars, gas, and even other black holes through their immense gravitational influence. Between these two extremes, intermediate black holes exist but remain elusive and difficult to study. These black holes weigh hundreds to thousands of times the mass of our Sun, sitting in a size gap between stellar and supermassive black holes. Their origins are still debated, with leading ideas suggesting they form from the merger of several smaller black holes or from the collapse of dense star clusters. Detecting intermediate black holes is challenging due to their relative rarity and the subtle signals they emit, but their discovery could fill important gaps in our understanding of black hole growth and galaxy evolution. Each type of black hole not only illustrates the power of gravity, but also provides insight into the life cycles of stars and the formation of galaxies. Supermassive black holes in particular are fundamental to the shaping of galaxies over cosmic time. Their gravitational pull influences the movement of stars, gas, and dust, helping to sculpt the overall structure of galaxies. But their impact goes beyond just gravity. Supermassive black holes can regulate star formation within their host galaxies. When these black holes pull in material, they sometimes emit intense jets and radiation that can heat surrounding gas, preventing it from cooling and condensing into new stars. This process acts as a cosmic thermostat, controlling the rate at which galaxies form stars. Sometimes the inflow of gas can trigger bursts of star formation nearby, while at other times, the energy output from the black hole suppresses star formation altogether. This delicate balance shapes the evolution of galaxies over billions of years. Furthermore, as galaxies collide and merge, a common event in the universe, the supermassive black holes at their centers often spiral towards each other and eventually merge. This cosmic dance releases gravitational waves, ripples in the fabric of space-time, carrying valuable information about these cataclysmic events across the cosmos. The merging of black holes also affects the orbits of stars around them, redistributing stellar material and altering the galaxy's overall shape. In exploring the different types of black holes, from the smallest stellar remnants to the colossal supermassive giants, we uncover the complex tapestry of cosmic phenomena that define our universe. These extraordinary objects not only test the limits of physics, but also illuminate the dynamic processes that govern the birth, life, and transformation of galaxies across the vast expanse of space and time. Furthermore, the study of supermassive black holes opens a remarkable window into the universe's past and its ongoing evolution. By carefully observing how these colossal entities grow and their intricate relationships with the formation of galaxies, scientists unlock crucial clues about the conditions that prevailed in the early cosmos. These cosmic giants don't just exist in isolation, they are deeply intertwined with the birth, growth, and transformation of galaxies throughout the vast stretches of time and space. As we explore the mysteries surrounding supermassive black holes, we uncover the delicate, interconnected web that binds together the universe's grand history, showing us how these fascinating phenomena have shaped the cosmic landscape we observe today. At the heart of each black hole lies a boundary known as the event horizon, a critical threshold marking the point of no return. Crossing this invisible frontier means plunging into a realm where the black hole's gravitational grip becomes so intense that nothing, not even light or matter, can escape. This very characteristic gives black holes their enigmatic and almost mythical reputation. For someone observing from outside this boundary, objects nearing the event horizon seem to slow dramatically, their signals taking longer and longer to reach the observer. This effect is caused by gravitational time dilation, a mind-bending phenomenon predicted by Einstein's theory of general relativity. From an outside perspective, the falling object appears to freeze and fade near the horizon, growing dimmer and increasingly redshifted until it vanishes from view. Yet, the experience is drastically different for the object itself. As it crosses the event horizon, it enters a realm dominated by extremes, where the fabric of space-time bends sharply under the weight of gravity. Beyond this point, the object is irresistibly drawn toward the singularity, a mysterious core where density is believed to reach infinity and where the known laws of physics collapse. This singularity challenges our understanding of reality at the most fundamental level, revealing a frontier where science encounters its greatest puzzles and paradoxes. One of the most captivating questions surrounding the event horizon concerns the fate of information. When matter is swallowed by a black hole, it seems to carry detailed information about its state into oblivion, raising the perplexing issue known as the black hole information paradox. Does this information truly disappear, violating the laws of quantum mechanics, or is it somehow preserved? This paradox has ignited intense debates among physicists, touching upon the core principles of quantum theory and gravitational physics. The event horizon, therefore, is not just a boundary in space. It is a focal point in the quest to unravel the fundamental workings of the universe. Detecting and studying black holes is a formidable challenge because these objects emit no light and remain invisible through direct observation. Instead, astronomers rely on indirect evidence to locate and understand them. One key method involves observing the gravitational effects a black hole exerts on nearby stars and gas clouds. By tracking the motions and orbits of these celestial neighbors, scientists can infer the mass and presence of an otherwise hidden black hole. Another crucial approach examines the intense radiation produced when matter spirals into a black hole, forming a blazing accretion disk heated to millions of degrees. This hot gas emits powerful X-rays and other high-energy radiation, which space-based observatories like the Chandra X-ray Observatory and the Event Horizon Telescope capture to provide vital insights into black hole behavior. The recent advances in capturing images near the edges of supermassive black holes mark a breakthrough in astronomy, allowing us to glimpse the extreme environments just beyond the event horizon. Moreover, the detection of gravitational waves, ripples in space-time caused by black hole collisions, has opened an entirely new window into these mysterious objects. Observatories such as the Laser Interferometer Gravitational Wave Observatory, LIGO, have recorded these subtle cosmic vibrations, giving researchers unprecedented information about how black holes merge and grow. This revolutionary technique enables scientists to study the population and dynamics of stellar mass black holes scattered throughout the universe, expanding our knowledge of their origins and the violent cosmic events that shape them. In essence, supermassive black holes serve as cosmic beacons, illuminating the dark corners of the universe's history and pushing the boundaries of human understanding. Through relentless observation and pioneering technology, we continue to unlock the secrets of these powerful phenomena, weaving together the story of the cosmos from the tiniest particle to the grandest galactic structures. Finally, theoretical models and computer simulations have become indispensable tools in the exploration of black holes. These models allow scientists to envision how black holes interact with their surrounding space and evolve through cosmic time. By integrating data collected from powerful telescopes and detectors with complex mathematical frameworks, astronomers assemble a vast cosmic puzzle that pushes the boundaries of our understanding. Each discovery challenges long-held ideas in physics, revealing new layers to the mysteries of the universe. As technology continues to advance and new methods of detecting these enigmatic objects emerge, the veil obscuring black holes is gradually lifted, revealing profound insights into the fabric of space and time. Neutron stars, on the other hand, are some of the densest and most extraordinary remnants left behind after massive stars end their lives in cataclysmic supernova explosions. These remnants form when a star, originally between 8 and 20 times the mass of our Sun, exhausts its nuclear fuel. The star's outer layers explode outward in a spectacular supernova, while the core collapses inward under the immense force of gravity. This implosion compresses matter to an extreme degree, turning the core into a neutron star, an object so dense that it defies ordinary comprehension. At the heart of a neutron star lies matter packed so tightly that protons and electrons fuse to become neutrons, creating a core almost entirely composed of these subatomic particles. Imagine compressing a mass greater than that of the Sun into a sphere roughly the size of a small city, about 10 kilometers across. The density is so immense that just a sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. This makes neutron stars among the most densely packed objects known in the cosmos. Beyond their staggering density, neutron stars exhibit remarkable and unusual behaviors. Many spin incredibly fast, rotating several times per second. These rapidly spinning neutron stars, known as pulsars, emit beams of intense radiation from their magnetic poles. As these beams sweep across space, if Earth happens to lie in the path, we observe periodic flashes of light, like a lighthouse casting its beam across the sea. These pulses offer scientists precious windows into the physics of matter under conditions impossible to recreate on Earth. Studying neutron stars not only deepens our understanding of how stars live and die, but also challenges our knowledge of nuclear physics and the fundamental forces operating at the smallest scales. The extreme environment inside neutron stars pushes the limits of our theories about how matter behaves under crushing pressure and density. Each new observation provides vital clues about the life cycles of stars and the very structure of matter itself. To put their density in perspective, neutron stars pack more mass than our Sun into a volume with a radius of about 10 kilometers. The density reaches hundreds of millions of grams per cubic centimeter, dwarfing the density of ordinary matter, and even that of atomic nuclei. For comparison, Earth's average density is about 5.5 grams per cubic centimeter, while neutron star matter exceeds this by a factor of millions. This extraordinary compression is a direct result of the gravitational forces acting on the collapsed core. In contrast, white dwarfs, the remnants of less massive stars, are significantly less dense. While white dwarfs may have densities around 100,000 times that of the Sun, they still pale in comparison to neutron stars. This stark difference highlights the extreme diversity of stellar remnants and the remarkable physics governing their formation and evolution. Through the lens of modern astronomy and astrophysics, neutron stars and black holes serve as cosmic laboratories, pushing humanity's quest to understand the universe's most profound mysteries. Their study opens doors to fundamental questions about gravity, matter, and the ultimate fate of stars. As researchers continue to unlock their secrets, these celestial objects reveal new chapters in the grand story of the cosmos. Additionally, neutron stars present an astonishing chapter in the story of stellar evolution, revealing a stage where matter reaches densities that even surpass those found in black holes, at least in certain respects. These compact remnants emerge from the violent deaths of massive stars, a transitional phase before some collapse further into black holes. Unlike black holes, which harbor a mysterious singularity at their core, where density is thought to become infinite and conventional physics breaks down, neutron stars maintain a delicate but well-defined structure. This balance is a cosmic tug-of-war between the immense gravitational forces pulling matter inward and the repulsive forces among densely packed neutrons resisting further collapse. Understanding the immense density of neutron stars is like peering into a cosmic laboratory where the laws of physics are pushed to their limits. These stars challenge our knowledge of nuclear interactions and the fundamental forces governing matter, offering clues not only about stellar evolution, but also about the behavior of matter under some of the most extreme conditions imaginable. The study of neutron stars thus serves as a bridge connecting the very large cosmic scales of galaxies and black holes with the incredibly small, the quantum realm of nuclear particles. Among the most fascinating neutron stars are pulsars, highly magnetized, rapidly spinning stellar remnants that emit beams of electromagnetic radiation like cosmic lighthouses. These beams sweep across space, and when aligned with Earth, they appear as remarkably regular pulses of radio waves, X-rays, or even gamma rays. Pulsars originate from the core remnants left behind after massive stars explode in spectacular supernovae, leaving behind incredibly dense objects with powerful magnetic fields and astonishing rotational speeds. The rotation of a pulsar, combined with its intense magnetic field, accelerates charged particles such as electrons along magnetic field lines that are often tilted relative to the star's spin axis. This acceleration generates beams of radiation spanning a broad spectrum of wavelengths. As these beams sweep past Earth, they create the characteristic pulsing signals that give pulsars their name and unique observational signature. These pulses can vary dramatically in their timing. Some spin hundreds of times per second, while others rotate more slowly. Yet many demonstrate an extraordinary regularity, making pulsars precise cosmic clocks. This precision transforms pulsars into powerful tools for astronomers. By measuring the timing of their pulses with incredible accuracy, scientists can investigate phenomena such as gravitational waves, ripples in the fabric of space and time, and the warping of space-time itself, predicted by Einstein's theory of general relativity. Some pulsars, known as millisecond pulsars, spin at dizzying speeds, sometimes hundreds of rotations per second. These are thought to have been recycled through the transfer of matter and angular momentum from a companion star, accelerating their spin to near breakneck speeds. The study of neutron stars and their pulsars deepens our understanding of the fundamental laws of physics, the behavior of matter under conditions that cannot be replicated on Earth, and the complex dance between stellar life cycles and the gravitational choreography of the universe. One of the most dramatic events involving neutron stars is their collision, known as a neutron star merger. When two neutron stars spiral together and collide, they unleash a cataclysmic explosion that generates intense gravitational waves, rippling through the cosmos and providing astronomers with a direct window into these enigmatic forces. These mergers not only offer a unique opportunity to test the predictions of general relativity, but also illuminate some of the universe's most profound mysteries. Among the most groundbreaking discoveries arising from neutron star mergers is their pivotal role in creating heavy elements. During these violent collisions, extreme energy and conditions facilitate a process called nucleosynthesis, the formation of atomic nuclei. Scientists believe these cosmic collisions are responsible for forging many of the universe's heaviest elements, including precious metals like gold and platinum, enriching the cosmos with the building blocks that eventually become part of planets and even life itself. By studying the electromagnetic radiation emitted before, during, and after these mergers, astronomers can decode the physical processes behind element creation, uncovering not just how the universe evolves on grand scales, but how the very matter that makes up our world came to be. Neutron stars, pulsars, and their spectacular mergers are thus not just exotic cosmic phenomena. They are keys to unlocking the deepest secrets of the universe, connecting the life cycles of stars with the fundamental forces shaping reality itself. Neutron star mergers open a window into some of the most extreme environments in the universe, offering unparalleled insights into the behavior of matter under crushing densities and immense pressures. When two neutron stars spiral into each other and merge, a complex dance of nuclear forces unfolds, forces so intense that they challenge our understanding of physics. This violent collision produces a spectacular astronomical event known as a kilonova. By carefully studying the light emitted from a kilonova, scientists gain a rare glimpse into the properties of nuclear matter pushed to its limits. The light spectrum from these kilonovae carries crucial clues about the strong nuclear force, the fundamental force that holds protons and neutrons tightly bound in atomic nuclei. Observations of these emissions allow researchers to refine models of how nuclear particles interact under conditions far beyond what can be replicated on Earth. But the importance of neutron star mergers extends beyond nuclear physics. These cosmic collisions also provide a novel way to measure the expansion rate of the universe. Thanks to the detection of gravitational waves, ripples in space-time caused by the merger, astronomers can calculate the distance to these events with unprecedented precision. Combining this data with measurements of how light stretches out, or redshifts, from the same source helps scientists pin down the value of the Hubble constant, the number that describes how fast the universe is expanding. Resolving discrepancies between different methods of measuring this constant is one of the great challenges in modern cosmology, and neutron star mergers are key players in this quest. Exploring neutron star mergers is like entering a rich laboratory where the laws of gravity, nuclear physics, and cosmic chemistry converge. Each discovery deepens our understanding of how elements are forged in the cosmos and how the universe itself evolves over billions of years. These stellar collisions remind us of the intricate, interconnected forces shaping the cosmos on the grandest scales. Among neutron stars, magnetars stand out as a remarkable and mysterious subclass. They possess magnetic fields so incredibly strong they defy ordinary comprehension, fields 1,000 times more powerful than those of typical neutron stars. Both magnetars and regular neutron stars are born from the catastrophic deaths of massive stars in supernova explosions. But magnetars distinguish themselves with magnetic fields that can reach strengths of around 1,000 million Teslas. To put this in perspective, this is about 1,000 times stronger than the magnetic field of an average neutron star. These colossal magnetic fields dramatically affect the behavior of magnetars. They unleash sudden, intense bursts of X-rays and gamma rays that can last anywhere from mere milliseconds to several hours. Such bursts are so powerful that astronomers can detect them across vast cosmic distances, providing precious insights into the nature of these exotic stars and their environments. While regular neutron stars can emit radiation, they rarely exhibit such explosive behavior. Instead, many are observed as pulsars, stars emitting beams of radiation with clockwork-like precision. The magnetic energy of a magnetar can also cause starquakes, violent shifts in the star's crust analogous to earthquakes on Earth. These seismic events release brief but powerful blasts of high-energy radiation. In contrast, the weaker, more stable magnetic fields of regular neutron stars generally prevent such magnetic-induced quakes. Both magnetars and ordinary neutron stars serve as invaluable natural laboratories, allowing scientists to study how matter behaves under the most extreme conditions imaginable. Understanding magnetars helps researchers explore the interplay between the strong nuclear force and intense magnetic fields, shedding light on the nature of matter at densities that far exceed anything experienced on Earth. By comparing the differences between magnetars and their less magnetic cousins, scientists gain a fuller picture of the life cycles of massive stars and the extraordinary phenomena that emerge throughout the universe. Detecting exoplanets, planets orbiting stars beyond our solar system, relies on a range of sophisticated techniques designed to reveal these distant worlds and uncover their secrets. One of the most common methods is the transit method. This technique monitors the subtle dimming of a star's brightness as a planet passes in front of it, temporarily blocking a small portion of its light. By analyzing the star's light curve, a graph of brightness over time, astronomers can determine vital details about the planet, such as its size, orbital period, and distance from its host star. Another powerful approach is the radial velocity method, also known as the Doppler method. This technique detects tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. As the star moves slightly toward us, its light shifts toward the blue end of the spectrum. As it moves away, the light shifts toward the red. Measuring these spectral shifts allows scientists to confirm the presence of planets and estimate their masses. Direct imaging of exoplanets is a more challenging, but increasingly fruitful technique. Since stars outshine their planets by enormous amounts, astronomers use advanced technologies like coronagraphs and star shades to block the starlight, making the faint glow of planets visible. These images can reveal information about an exoplanet's atmosphere and even hint at surface conditions, offering tantalizing clues about worlds far beyond our own. Together, these methods have transformed our understanding of planetary systems across the galaxy, revealing a dazzling diversity of planets and fueling our quest to find potentially habitable worlds among the stars. Additionally, gravitational microlensing presents a remarkable and innovative technique for detecting distant exoplanets, opening a window into worlds far beyond our reach. When a massive object such as a star crosses directly in front of a more distant star, the immense gravitational field of the foreground star bends and magnifies the light from the background star, much like a cosmic lens. This bending of light, predicted by Einstein's theory of general relativity, temporarily brightens the background star in a distinctive pattern. If the foreground star happens to host a planet orbiting around it, that planet can cause additional subtle changes in the light pattern, signaling its presence, even though the planet itself cannot be seen directly. This method proves especially valuable for uncovering exoplanets that orbit far from their parent stars, regions often inaccessible by other detection techniques like transit photometry or radial velocity. Gravitational microlensing, therefore, expands our ability to find planets in a diverse range of orbits, helping us piece together a broader picture of planetary systems throughout the galaxy. Across the past few decades, the variety of techniques developed for detecting exoplanets has revolutionized our understanding of planets beyond the solar system. These methods, including radial velocity, transit detection, direct imaging, and microlensing, have revealed a stunning diversity of exoplanets, with sizes ranging from smaller than Earth to several times the size of Jupiter, compositions that vary from rocky to gaseous, and orbital behaviors that defy earlier assumptions. As telescopes and observational technology grow more sophisticated, such as with the deployment of powerful space observatories and advanced ground-based instruments, the search for exoplanets continues to accelerate, uncovering ever more surprising and complex worlds. Each new discovery enriches our knowledge not only of where planets exist, but also of the processes that form and shape planetary systems. This quest also fuels humanity's hope of finding life beyond Earth by identifying worlds with environments that might support it. Among the many fascinating types of exoplanets discovered, one of the most common and intriguing categories is the so-called hot Jupiters. These are gas giant planets roughly the size of Jupiter, but unlike the gas giants in our solar system, they orbit extremely close to their parent stars. This proximity subjects them to intense stellar radiation, resulting in scorching surface temperatures and incredibly short orbital periods, often completing a full orbit in just a few days. The existence of hot Jupiters challenged traditional models of planetary formation, which predicted that gas giants should form far from their stars in the cold outer regions of the protoplanetary disk where ices can condense. Another prominent class is the super-Earths, rocky planets with masses larger than Earth's but smaller than that of Neptune. These planets display a wide variety of compositions. Some may have thick atmospheres, while others might be predominantly rocky. The discovery of super-Earths has broadened the concept of potentially habitable planets because some of these worlds could possess conditions suitable for life depending on their atmospheres, temperatures, and other factors. Super-Earths highlight the incredible diversity of planets and raise exciting questions about their potential habitability. Closely related to super-Earths are the mini-Neptunes, planets smaller than Neptune but larger than Earth. These worlds often feature thick atmospheres composed of a mixture of gases and ices, giving them characteristics that lie somewhere between terrestrial planets and gas giants. The abundance of mini-Neptunes among detected exoplanets has sparked ongoing research into how such planets form and evolve, as well as their atmospheric dynamics, which differ significantly from those of both Earth-like and giant planets. In addition to these, astronomers have identified terrestrial planets more akin to Earth and Venus, smaller, rocky worlds that are particularly challenging to detect due to their modest sizes. Some of these terrestrial exoplanets reside within the habitable zone of their stars, where temperatures might allow liquid water to persist on their surfaces, a key ingredient for life as we know it. The discovery of such planets intensifies the search for extraterrestrial life by focusing attention on worlds where biological activity could potentially flourish. The incredible diversity of exoplanets discovered so far paints a vivid picture of the complexity and richness of planetary systems scattered across the universe. Each new finding offers vital clues about the formation, migration, and evolution of planets, challenging astronomers to continually refine their theories and models. The unfolding story of exoplanet exploration is far from complete. With future missions and improved technology, astronomers eagerly anticipate unveiling even more extraordinary worlds, deepening our understanding of the cosmos and our place within it. Central to the search for life beyond Earth is the concept of the habitable zone, often called the Goldilocks zone. This is the region around a star where conditions are just right for liquid water to exist on the surface of a planet, not too hot and not too cold. The precise boundaries of this zone depend on the star's size and temperature, meaning that habitable zones vary widely among different star systems. Identifying planets within this zone is a critical step in narrowing the search for life, as liquid water is considered essential for life as we understand it. However, being located in the habitable zone alone does not guarantee that a planet can support life. Other critical factors influence a planet's habitability, including its atmospheric composition, surface pressure, magnetic field, and geological activity. For example, a planet too close to its star may suffer from extreme heat and harmful radiation that strip away its atmosphere, while a planet too far may be frozen solid, unable to sustain liquid water. These complex interactions make the study of habitability a multi-dimensional challenge. Understanding the habitable zone allows scientists to prioritize which exoplanets to study in greater detail, focusing on those most likely to host life. Yet, researchers also consider life in more extreme environments beyond the traditional habitable zone. Some moons and planets may harbor subsurface oceans beneath thick ice layers or experience strong greenhouse effects that keep them warm despite their distance from their star. These possibilities broaden the scope of astrobiology, reminding us that life might thrive in environments vastly different from Earth's. The exploration of exoplanets and their varied characteristics represents one of the most thrilling frontiers in modern astronomy. As we push the boundaries of technology and observation, we continue to reveal the incredible variety of worlds that populate our galaxy and the potential they hold to answer one of humanity's most profound questions. Are we alone in the universe? Moreover, delving into the characteristics of planets situated within the habitable zone unlocks crucial insights into planetary climates and atmospheres, insights that are indispensable for evaluating a planet's potential to support life. By examining factors such as the presence of greenhouse gases, magnetic fields, and the planet's geological history, scientists can piece together a clearer picture of what makes a world truly suitable for life as we understand it. This exploration of the habitable zone stands as a foundational pillar in the field of astrobiology, steering researchers toward answers to some of humanity's most profound questions. Are we alone in the universe? Does life exist beyond Earth? The search for biosignatures on exoplanets, planets orbiting stars beyond our solar system, centers on identifying specific chemical and physical markers that might hint at biological activity. To accomplish this, astronomers deploy an array of sophisticated techniques and cutting-edge technology to analyze the atmospheres and surfaces of these distant worlds. One of the most powerful tools in their arsenal is spectroscopy, a method that deciphers the light spectrum emitted or absorbed by a planet's atmosphere during a transit event when the planet passes in front of its host star from our vantage point. As starlight filters through the thin atmospheric layers of the planet, it interacts with molecules present there, absorbing light at certain wavelengths unique to those chemicals. Scientists scrutinize these absorption patterns, searching for gases considered potential biosignatures, such as oxygen, methane, carbon dioxide, and ozone. The detection of free oxygen, or more compellingly, a simultaneous presence of oxygen and methane, is especially tantalizing. These gases tend to chemically react with one another and would not coexist for long without a continuous replenishing source, suggesting ongoing biological processes. Beyond atmospheric clues, researchers are also deeply interested in surface conditions that could indicate life's presence. For example, evidence of liquid water, perhaps in oceans, lakes, or subsurface reservoirs, is a powerful signal of potential habitability, since water is essential for life as we know it. Remote sensing technologies allow scientists to gather detailed information about distant planets without physically visiting them. By measuring characteristics like surface temperature, geological activity, and planetary composition, researchers gain insight into the environmental conditions that might sustain life. Studying exoplanets specifically located in the habitable zone, where temperatures permit the existence of liquid water, enhances the chances of finding genuine biosignatures. Additional factors such as geological activity, which can recycle essential nutrients, and magnetic fields, which shield a planet from harmful cosmic radiation, are also critical components in determining a planet's suitability for life. As observational technology rapidly advances, with new instruments such as the James Webb Space Telescope leading the way, our ability to collect high-resolution data about exoplanet atmospheres and surfaces is improving dramatically. This progress empowers scientists to conduct increasingly detailed studies that bring us closer to unraveling the mysteries of extraterrestrial life. The quest to identify biosignatures not only fuels scientific discovery, but could also transform our understanding of the cosmos and humanity's place within it. Among the most promising candidates for potential life are planets located within the habitable zones of their stars. One notable example is Proxima Centauri b, a planet orbiting the red dwarf star Proxima Centauri, which lies just over 4 light-years from Earth. Roughly Earth-sized and comfortably positioned within its star's habitable zone, this exoplanet has captured intense interest for its prospects of hosting life. Another compelling world is Kepler 186f, discovered by NASA's Kepler Space Telescope. Slightly larger than Earth and orbiting within the habitable zone of its star Kepler 186, this planet is part of a multi-planet system, offering a unique opportunity to study how different planetary environments might interact and affect habitability. Then there is the remarkable TRAPPIST-1 system, which boasts 7 Earth-sized planets orbiting a cool dwarf star. 3 of these planets reside within the habitable zone, making this system particularly fascinating. The diverse conditions present on these worlds raise the exciting possibility that not just one, but several planets in the system could harbor environments conducive to life. This discovery has invigorated the scientific community and the public alike, as it represents one of the most promising avenues in our ongoing search for life beyond our solar system. Additionally, there is LHS 1140b, an exoplanet located about 41 light-years from Earth. This fascinating world is notably larger than our own planet, but still orbits within the habitable zone of its star, the region where conditions might allow liquid water to exist on the surface. Classified as a rocky planet, LHS 1140b has captured the attention of scientists worldwide because of its potential to support life. Its unique features, such as its size, composition, and position, make it an exciting subject for ongoing research as technology continues to evolve. These distant, intriguing planets invite us to look beyond our solar system and explore the countless possibilities for life in the cosmos. Stars themselves begin their extraordinary journey within vast, cold clouds of interstellar gas and dust, mostly made up of hydrogen molecules. Over time, certain regions inside these enormous clouds experience gravitational collapse. Often, small disturbances like shock waves from nearby supernovae trigger denser pockets within the cloud to start condensing. As gravity draws the gas and dust inward, the material clumps together, forming dense cores. These cores gradually grow more compact and hotter due to the immense pressure squeezing them from all sides. This critical early phase is known as the protostar stage. During the protostar phase, the forming star continues to gather surrounding gas and dust, increasing its mass and internal temperature. When the core temperature finally climbs to millions of degrees, nuclear fusion reactions ignite. This moment signals the birth of a new star as hydrogen atoms fuse to create helium, releasing vast amounts of energy that make the star shine. However, not all of the cloud's material becomes part of the star itself. Some of it flattens into a rotating disk around the newborn star, setting the stage for the eventual formation of planets, moons, and other celestial bodies. Powerful stellar winds, streams of particles flowing out along the star's rotational axis, also blow away leftover gas and dust, clearing the way for this cosmic construction to continue. This entire star formation process spans millions of years, during which the star grows in mass and stabilizes. Once it reaches a steady phase on the main sequence of the Hertzsprung-Russell diagram, a fundamental tool astronomers use to classify stars, it settles into a long period of brightness and energy output. It is during this time that the star provides the stable conditions necessary for life to potentially develop on any nearby planets. Thus, the cycle of stellar birth shapes not only individual stars, but also the fate and architecture of entire solar systems. The lifespan and ultimate destiny of a star are primarily determined by its mass. A star's mass influences the core temperature, pressure, and the rate at which it burns through its nuclear fuel. More massive stars consume their hydrogen fuel at a much faster rate than smaller stars, leading to significantly shorter lifespans. For example, a star like our Sun is expected to live about 10 billion years, while a massive star might exhaust its fuel in just a few million years. As a star evolves, it undergoes dramatic transformations. When the hydrogen in its core is depleted, the star expands into a red giant. In this phase, the core contracts and heats up, igniting fusion in the surrounding shell of hydrogen, which converts into helium. This causes the star's outer layers to balloon outward, dramatically increasing its brightness and size. Eventually, the star sheds these outer layers, creating a glowing shell of gas known as a planetary nebula. What remains behind is a dense, cooling core called a white dwarf. For the most massive stars, however, the story ends in a far more violent and spectacular way. After fusing heavier elements in their cores, these stars can explode in an immense supernova. This cataclysmic event occurs when the core collapses under its own gravity, causing a massive rebound that blasts the star's outer layers into space at incredible speeds. The explosion is so powerful that it creates conditions where even heavier elements can form. Depending on the remaining core's mass, the aftermath may be a neutron star or, if massive enough, a black hole. The journey of a star, from its quiet birth in a molecular cloud to its often spectacular death, is profoundly shaped by its original mass. Smaller stars typically end their lives gently as white dwarfs, while massive stars produce some of the universe's most exotic objects, including neutron stars and black holes. This complex dance of mass, energy, and nuclear processes governs the life cycle of stars and their lasting impact on the cosmos. Supernovae play a crucial role in enriching the universe chemically. When a massive star reaches the end of its life, the supernova explosion scatters heavy elements far and wide. Before the explosion, elements such as helium, carbon, nitrogen, and oxygen build up in the star's core through nuclear fusion. The supernova then disperses these elements into space, and through rapid neutron capture, a process called R-process nucleosynthesis, it also creates even heavier elements like iron, gold, and uranium. The heavy elements ejected by supernovae mix with the surrounding interstellar medium, the gas and dust between stars. This material becomes part of new clouds that will eventually collapse to form new stars and planetary systems. Thanks to this cosmic recycling, each generation of stars and planets is enriched with elements from previous stellar explosions. These elements are essential not only for the physical structure of planets, but also for the chemical complexity that makes life possible. In this grand cycle of stellar birth, death, and rebirth, supernovae act as the universe's great alchemists. They forge the building blocks of planets and life, scattering them across the cosmos. Through their violent deaths, stars contribute to the continuous renewal and evolution of the universe, ensuring that the elements necessary for life are passed down from one generation of stars to the next. This cosmic recycling process is fundamental to the ever-changing tapestry of the night sky and the ongoing story of existence itself. The universe unfolds as a vast and intricate tapestry, woven from countless elemental threads, each one shaping the chemical foundations of future generations of stars, planets, and even life itself. Every supernova explosion acts as a critical chapter in the ongoing saga of cosmic evolution, dispersing the essential building blocks that seed the cosmos with complexity and diversity. Among the many celestial actors in this grand story, brown dwarfs occupy a mysterious and compelling role, existing in a realm between the largest planets and the smallest stars. Often labeled as failed stars, these objects form much like true stars do, emerging from collapsing clouds of gas and dust, but they fall short of igniting the powerful nuclear fusion of hydrogen in their cores, a process that defines a star's very essence. Typically, a brown dwarf carries a mass anywhere from about 13 to 80 times that of Jupiter. This makes them significantly more massive than even the largest gas giants, yet still insufficiently heavy to sustain the continuous nuclear reactions that illuminate stars for billions of years. The key difference between brown dwarfs and stars lies deep within their cores. Stars reach temperatures and pressures high enough to fuse hydrogen into helium, generating a steady flow of energy. Brown dwarfs, however, fail to reach these extreme conditions. Instead, they produce energy through the fusion of deuterium, a heavier isotope of hydrogen, early in their lives, followed by the burning of lithium. Both of these processes are fleeting. Once these fuels are exhausted, brown dwarfs gradually cool, fading into darkness over time. Because brown dwarfs emit most of their light in the infrared spectrum rather than visible light, they are notoriously difficult to detect with conventional optical telescopes. Their faint glow often remains hidden in the cosmic shadows cast by their brighter stellar neighbors. Yet the study of brown dwarfs pushes the boundaries of how astronomers define the line between stars and planets, challenging traditional categories and prompting deeper investigation into the formation and evolution of celestial bodies. By understanding these enigmatic objects, scientists bridge the gap between full-fledged stars and planetary systems, revealing the remarkable diversity and complexity of the universe. In a parallel cosmic dance, binary and multiple star systems arise from similar processes but add layers of complexity. These systems form in giant molecular clouds, vast regions of gas and dust permeating galaxies, where gravitational instabilities cause dense pockets of matter to collapse. Often, a single collapsing region fragments into two or more clumps. each destined to become a star. This fragmentation, driven by turbulence and the specific conditions within the cloud, determines whether a system will contain two stars locked in mutual orbit or multiple stars entwined in a more intricate gravitational web. Within binary systems, the two stars revolve around each other, their gravitational pull intertwining their fates. Such interactions can lead to phenomena like mass transfer, where material flows from one star to the other as one evolves faster. This exchange can dramatically alter the structure and behavior of both stars, sometimes culminating in explosive events such as novae or even supernovae. When a red giant star overflows its outer layers onto a companion, the cosmic consequences can be profound. In multiple star systems, these gravitational interactions become even more complex, often forming hierarchical arrangements where pairs of stars orbit around other stars. Over time, these gravitational forces can shift orbits, altering the dynamics of the entire system. The evolutionary outcomes for stars in these systems vary widely. Some may end their lives as supernova, scattering their enriched material across space, while others settle into quieter endings as white dwarfs, neutron stars, or black holes. The presence of multiple stars in close proximity also impacts planet formation, as the complex gravitational environment can disrupt the stable orbits necessary for planets to form and thrive. Studying binary and multiple star systems provides astronomers with invaluable insights into the processes governing star formation, stellar evolution, and the gravitational choreography that shapes the cosmos. On an even grander scale, galaxies themselves emerge and evolve through a saga stretching back to the dawn of time, soon after the Big Bang. Initially, the universe was a hot, dense sea of particles, but as it expanded and cooled, tiny fluctuations in density sparked a chain reaction. Regions rich in gas and dark matter began to clump together, drawn by gravity's relentless pull. Over billions of years, these clumps merged and grew, giving rise to the galaxies that dot our universe today, a spectacular testament to the power of cosmic forces sculpting matter into the grand structures we observe. This unfolding cosmic story, from the faint glow of brown dwarfs to the complex dances of binary stars and the majestic formation of galaxies, continues to captivate astronomers. Each discovery enriches our understanding of the universe's boundless diversity, revealing a cosmos alive with dynamic processes and endless wonder. These immense gravitational forces set in motion a cosmic dance that shaped the very fabric of the early universe. Vast clouds of primordial gas, once spread thin and diffuse, began to collapse under their own gravity. This collapse caused these immense gas clouds to clump together, forming the universe's very first stars. As these ancient stars ignited, their cores became powerful furnaces, fusing hydrogen atoms into heavier elements like helium, carbon, and beyond. This process, known as nuclear fusion, did more than produce light and heat. It enriched the surrounding gas with new, heavier elements, seeding the cosmos with the building blocks for future generations of stars, planets, and ultimately, life itself. The birth of galaxies unfolded in a dramatic two-act saga. First came the collapse of matter into what scientists call proto-galaxies, vast and chaotic regions where gravity pulled together gas, dust, and dark matter. These proto-galaxies, colossal in scale, ignited intense bursts of star formation. The radiation from these newborn stars heated their surroundings, stirring turbulence in the gas clouds and triggering the birth of even more stars. Over time, the relentless pull of gravity gathered more gas and dark matter, causing these proto-galaxies to grow and merge. This process, known as hierarchical clustering, saw small, irregular structures gradually come together, building up the large, majestic galaxies we observe today. As galaxies evolved, they transformed through a series of cosmic events that altered their shapes and contents. Collisions and mergers between galaxies, cataclysmic events spanning millions of years, could trigger dramatic bursts of star formation, reshape galactic structures, or even fuse two spiral galaxies into a smooth elliptical form. The intricate gravitational interplay between galaxies, shaped largely by the invisible yet dominant presence of dark matter, governs much of their behavior. Dark matter acts as a cosmic scaffold, influencing how galaxies attract and pull on one another, shaping their paths across the vast expanse of space. Over billions of years, galaxies continued their evolution, influenced by complex factors such as star form rates, the explosive deaths of stars called supernovae, and the presence of supermassive black holes nestled in their centers. These black holes, some billions of times the mass of our Sun, can regulate their host galaxy's growth through powerful feedback mechanisms, including energetic jets and radiation that can heat or expel gas. The balance between gas inflow, star formation, and gas outflow driven by these and other processes determines how rapidly a galaxy changes and what shape it ultimately takes. Studying the formation and evolution of galaxies offers astronomers a window into the grand story of the universe. This cosmic narrative reveals the deep connections between galaxies, the stars they birth, and the dark matter that holds them all together, weaving an intricate tapestry of cosmic history. Galaxies are classified into several main types based on their shape, structure, and formation history, each with distinct characteristics that tell a unique story. Spiral galaxies like our own Milky Way and the nearby Andromeda Galaxy are some of the most visually stunning. They feature flat, rotating disks filled with stars, gas, and dust, organized into graceful spiral arms that wind outward from a dense central bulge. These arms are bustling regions of ongoing star formation, home to young, bright stars that shine in vibrant blues and whites. In contrast, the central bulge contains older, redder stars. At the heart of many spiral galaxies lies a supermassive black hole, whose immense gravity influences the galaxy's overall dynamics and evolution. Elliptical galaxies, by contrast, display a wide range of shapes, from nearly perfect spheres to elongated ellipsoids. These galaxies are dominated by older, red stars and typically contain very little gas or dust, resulting in minimal new star formation. Many elliptical galaxies reside in dense clusters where gravitational interactions and mergers strip away gas and cause stars to collide and combine. Often considered the end products of galaxy evolution, ellipticals may have formed through the merging of smaller galaxies over time. Irregular galaxies defy simple classification. Lacking a defined shape or structure, they often appear chaotic and scattered. These galaxies are rich in gas and dust, fueling high rates of star formation. Their irregular forms often result from gravitational interactions or past mergers with neighboring galaxies that have distorted their original shapes. Famous examples include the Large and Small Magellanic Clouds, satellite galaxies orbiting the Milky Way, visible to the naked eye from the southern hemisphere. Finally, lenticular galaxies occupy a transitional category, bridging the gap between spirals and ellipticals. They feature a prominent central bulge, like ellipticals, but also possess a disk component reminiscent of spiral galaxies. Lenticular galaxies are often seen as a snapshot of galactic evolution in progress, reflecting the complex interplay of forces shaping the universe. Through the detailed study of these diverse galaxy types, astronomers continue to unravel the mysteries of how the universe's vast structures formed, grew, and evolved, illuminating the cosmic origins of the stars, planets, and life that fill the cosmos today. However, lenticular galaxies present a fascinating blend of characteristics that place them in a unique position within the cosmic landscape. Unlike their spiral counterparts, lenticular galaxies exhibit only a limited spiral structure and show relatively low rates of star formation. This suggests that they occupy a transitional phase in the grand evolutionary journey of galaxies. Their distinct presence of a significant central bulge combined with a disk-like shape allows them to share features with both spiral and elliptical galaxies, making them intriguing subjects for astronomers studying galactic evolution. The wide variety of galaxy types scattered across the universe offers profound insights into the complex processes governing stellar formation, cosmic evolution, and the vast web of gravitational interactions shaping everything on a colossal scale. Understanding the differences among these galactic forms helps scientists piece together the history of the cosmos and decipher the critical roles each galaxy plays in the larger cosmic tapestry. One of the most dramatic and transformative forces shaping galaxies is the interaction and collision between them. When galaxies draw near to one another, their mutual gravitational forces set in motion intricate dynamics that can dramatically alter their structure and future. During these cosmic encounters, intense tidal forces tug at their shapes, sometimes stretching and distorting them in breathtaking ways. These gravitational interactions often ignite bursts of star formation in regions where clouds of gas collide and compress, sparking new stellar nurseries. A particularly striking outcome of galaxy collisions is the profound alteration of their internal structure. For example, when two spiral galaxies collide, the resulting gravitational turmoil can destroy the orderly spiral arms and eventually form a more rounded, smoother shape known as an elliptical galaxy. This transformation is a result of the chaotic redistribution of stars and gas as gravitational energy reshapes the galaxy into a more homogeneous form without the distinct features of spirals. The ultimate fate of colliding galaxies depends heavily on factors such as their relative masses, speeds, and the angles at which they meet. These parameters influence whether the galaxies will merge into a single entity or continue interacting over extended periods, sometimes leading to repeated encounters. Beyond reshaping structures, mergers play a vital role in enriching the galaxy's interstellar medium with heavier elements. During these colossal cosmic events, supernova explosions often occur in both colliding galaxies, spewing massive amounts of heavy elements like iron and oxygen into surrounding gas. This enriched material serves as the foundation for the next generation of stars, continuing the endless cycle of stellar birth and death. In cases where one of the merging galaxies houses a supermassive black hole at its core, the collision can awaken this cosmic giant. The influx of matter during the merger can stimulate intense activity, sometimes leading to the formation of active galactic nuclei, powerful sources of radiation that can outshine entire galaxies. The repercussions of galaxy collisions extend beyond individual galaxies and can influence entire groups and clusters. When multiple galaxies merge within a cluster, these events can set off a cascade of gravitational interactions, affecting the orbits of other cluster members and even altering the distribution of elusive dark matter within the cluster. This intricate gravitational dance highlights the profound importance of mergers and collisions in the broader narrative of galactic evolution, adding essential chapters to the ongoing story of the universe. Galaxy clusters themselves are among the largest gravitationally bound structures known, consisting of hundreds to thousands of galaxies held together by gravity. These immense assemblies serve as natural laboratories for studying cosmic evolution, dark matter, and the large-scale structure of the universe. Within a typical cluster, galaxies coexist alongside vast reservoirs of hot, X-ray emitting gas and vast amounts of dark matter, which together make up a significant portion of the cluster's total mass. The formation of galaxy clusters traces back to the earliest epochs following the Big Bang, unfolding over billions of years. Initially, tiny fluctuations in the density of matter in the early universe began to grow under the influence of gravity. Dark matter, although invisible, played a crucial role by exerting gravitational pull that attracted gas and ordinary matter. Regions with slightly higher densities gathered more mass, sparking a hierarchical growth process where small structures merged to form larger groups, eventually building massive clusters. As galaxy clusters grew, the interactions and mergers within them became more frequent and complex. These gravitational encounters triggered evolutionary changes among member galaxies, often transforming their shapes and properties. The relentless dance of gravity within clusters continuously sculpts the galaxies, enriching our understanding of cosmic history and the dynamic forces that shape the universe we observe today. Additionally, the hot gas found within galaxy clusters, often detected as X-ray emitting plasma, plays a crucial role in shaping the dynamics of these colossal cosmic gatherings. This searing gas doesn't just float around passively, it interacts deeply with the galaxies embedded in the cluster. The intricate relationship between galaxies and this surrounding hot plasma directly influences star formation rates, which in turn impacts the ultimate fate of galaxies residing in these clusters. Galaxy clusters, beyond being mere collections of galaxies, serve as cosmic laboratories that provide vital clues about some of the universe's most profound mysteries, including dark matter and the very geometry of the cosmos. Through detailed observations, particularly via gravitational lensing effects, astronomers can peer into the hidden scaffolding of the universe. Gravitational lensing occurs when the immense gravity of a galaxy cluster bends the light coming from even more distant galaxies behind it. This bending distorts the images of those background galaxies into arcs and multiple images, acting as a natural magnifying glass. By analyzing these distortions, scientists can create detailed maps of dark matter, the invisible substance that neither emits, absorbs, nor reflects light, making it undetectable through conventional telescopes. Yet its presence is undeniable due to the gravitational influence it exerts on visible matter and hot gas in clusters. These maps reveal how dark matter is distributed across enormous cosmic structures, confirming that it dominates the mass-energy budget of the universe. Studying the properties of galaxy clusters helps astronomers trace how large-scale structures have evolved over billions of years. This allows them to refine models of cosmic evolution and deepen their understanding of the fundamental forces governing the universe's behavior. Galaxy clusters are especially powerful in studying both dark matter and dark energy. Dark energy, the mysterious force thought to drive the accelerated expansion of the universe, leaves its fingerprints in the formation and distribution of galaxy clusters. By observing how many clusters exist at different epochs and how their characteristics change over time, researchers gain valuable insights into the interplay between mass, expansion, and dark energy. The rate at which clusters form and grow can help scientists understand the properties of dark energy and its impact on the universe's overall dynamics. Complementing these studies is the cosmic microwave background radiation, the afterglow of the Big Bang. Detailed measurements of tiny fluctuations in this ancient light provide further clues about the large-scale structure of the cosmos, including the distribution of galaxy clusters. When combined with gravitational lensing and cluster observations, these tools offer a comprehensive picture of how dark matter and dark energy interact, guiding us toward a deeper grasp of the universe's composition and ultimate destiny. Beyond clusters, cosmic voids form another fascinating feature of the universe's large-scale structure. These vast, nearly empty regions contain far fewer galaxies than average and can span from tens to hundreds of millions of light-years in diameter. Despite their emptiness, cosmic voids are essential in shaping the universe's architecture and influencing how galaxies form and spread out. The birth of these voids traces back to the earliest moments after the Big Bang, during a period called cosmic inflation. Tiny quantum fluctuations in the density of matter caused slight variations across space. Over billions of years, gravity amplified these variations, pulling matter together into dense filaments and clusters, while leaving other regions relatively empty. These emptier regions expanded into the cosmic voids we observe today, illustrating how the universe's vast and intricate web of matter came to be. Together, the study of hot gas and galaxy clusters, the elusive dark matter, the enigmatic dark energy, and the immense cosmic voids forms a grand narrative, one that reveals the ongoing story of the universe's formation, evolution, and future. These cosmic structures and phenomena are the keys to unlocking the deepest questions about our universe's nature and fate. In the vast cosmic web that defines the structure of our universe, matter arranges itself into an intricate network of filaments, sheets, and clusters, interwoven in a grand cosmic tapestry. These sprawling formations are punctuated by enormous regions nearly devoid of significant matter, known as cosmic voids. As galaxies formed and gathered together under the relentless pull of gravity, the spaces between these dense clusters expanded, creating these vast cosmic voids. Immense, nearly empty expanses that hold the quiet echoes of the universe's ancient past. Cosmic voids stand out for their unique dynamics. Unlike the bustling hubs of galaxies and clusters, these voids feature much lower matter densities and experience a slower rate of gravitational attraction. This allows them to expand and grow larger over time, essentially becoming fossils that preserve clues about the universe's history and evolution. By studying cosmic voids, scientists gain a rare window into the elusive forces of dark energy and dark matter, as the shape, size, and distribution of these voids directly reflect the underlying behavior of these mysterious components. Observing how voids evolve and interact within the cosmic web helps astronomers piece together the grand story of cosmic evolution and the fundamental fabric of spacetime. Far from being empty nothingness, cosmic voids play a critical role in shaping the universe's large-scale architecture. They influence the distribution of matter by creating a framework within which filaments, clusters, and sheets organize. The gravitational effects near voids subtly alter the motions of galaxies located along their edges. While galaxies inside dense clusters experience intense gravitational interactions, those on the outskirts of voids often move away from these empty spaces, leading to peculiar velocities that affect their formation and development. This gravitational interplay impacts not only galaxy dynamics, but also the star formation rates within these environments. Because voids contain less gas, the raw material for stars, galaxies residing within them tend to have lower rates of star formation and may follow evolutionary paths quite different from their denser counterparts. This diversity in galactic environments enriches the variety of galaxy types we observe across the cosmos. Understanding cosmic voids also advances our grasp of dark matter and dark energy, two of the greatest enigmas in modern cosmology. These voids respond sensitively to the expansion of the universe driven by dark energy, and their evolving shapes and sizes allow researchers to refine models of cosmic evolution. By analyzing the geometry and distribution of voids, astronomers can test competing theories about how the universe expands and how large-scale structures form over billions of years. In this sense, cosmic voids are not just empty spaces, but vital pieces in the puzzle of how the universe works. Interwoven through the cosmic web are colossal thread-like structures known as cosmic filaments. Composed of galaxies, gas, and dark matter, these filaments form the skeleton of the universe's large-scale structure. Stretching across hundreds of millions of light years, they connect galaxy clusters like vast cosmic highways, guiding the flow of matter across immense distances. The cosmic web, made up of filaments, walls, and voids, represents the largest known organization of matter, sculpted by gravity since the Big Bang. After the initial explosion that birthed the universe, tiny quantum fluctuations in matter density were amplified by gravity, causing matter to clump together into the filaments we observe today. Dark matter plays a crucial role here, acting as a gravitational scaffold around which visible matter gathers, allowing galaxies to form along these filaments while cosmic voids open up between them. The formation of cosmic filaments is tightly linked to hierarchical clustering, a process where smaller structures merge over time to create larger ones. As matter flows along filaments, galaxies and gas accumulate at filament intersections, forming massive galaxy clusters. Meanwhile, the low-density voids between filaments provide contrasting environments, making the cosmic web a dynamic arena for galaxy evolution. This network facilitates not only the movement of galaxies, but also the transfer of gas and dark matter, processes essential for star formation and the growth of galaxies. By studying cosmic filaments, astronomers gain critical insights into the fundamental forces shaping the universe. The characteristics and evolution of these filaments reveal how dark matter and dark energy influence cosmic dynamics, offering a clearer picture of the forces governing the cosmos. The galaxies and clusters that populate cosmic filaments do so in a pattern that reflects the universe's underlying structure. Gravitational forces cause matter to gather in regions of higher density, resulting in the formation of galaxy clusters at the intersections of filaments, while the filaments themselves maintain a higher density than the surrounding cosmic voids. Galaxies along these filaments exhibit a rich diversity. Spiral, elliptical, and irregular types coexist, shaped by the environmental conditions unique to their locations. The gravitational influence of filaments not only governs galaxy distribution, but also affects their evolution. Galaxies near filaments often experience different interactions compared to those isolated in voids, influencing their star formation rates and overall development. At the nodes or junctions of these filaments lie galaxy clusters, some of the largest gravitationally bound structures in the universe. These clusters act as dense hubs where gravitational attraction pulls galaxies and matter into tight assemblies. The presence of such clusters profoundly influences the surrounding galaxies, regulating processes like star formation and gas retention. In this way, galaxy clusters contribute to the complex ecosystem of the cosmic web, where matter is continually reshaped by the forces of gravity, dark matter, and dark energy. Together, Cosmic voids, filaments, and clusters compose a vast, interconnected network, the cosmic web, that forms the grand architecture of our universe. Studying these colossal structures not only reveals how matter is distributed across unimaginable distances, but also unlocks the secrets of the fundamental forces that drive cosmic evolution. Through the lens of the cosmic web, humanity glimpses the extraordinary story of the universe's past, present, and future, an epic woven into the fabric of space and time itself. Furthermore, the distribution of galaxies along the vast cosmic filaments plays an essential and transformative role in shaping the grand dynamics of the universe. These cosmic filaments act as immense bridges, weaving together clusters of galaxies across unimaginable distances. By connecting these colossal clusters, the filaments facilitate the continuous flow of matter, both ordinary gas and elusive dark matter, moving seamlessly between different regions of space. This extraordinary interconnectedness doesn't just dictate the large-scale arrangement of galaxies, it profoundly influences critical cosmic processes, including galaxy formation, star birth, and the cycling of gases within clusters. Delving into how galaxies and clusters align along these filaments grants astronomers a clearer, more comprehensive view of the universe's evolution and the fundamental forces molding the enormous structure of cosmic matter. Cosmic voids and filaments offer some of the most vital clues to understanding the intricate architecture of the cosmos. Cosmic voids, which are expansive regions almost entirely devoid of galaxies, constitute roughly 80% of the universe's volume. These vast empty spaces act much like cosmic deserts, starkly contrasting with the dense, bustling clusters of galaxies that surround them. Void regions help scientists grasp the nature of gravitational forces that sculpt the universe on the largest scales. By studying these emptier spaces, researchers uncover essential details about how matter is distributed and how that distribution has changed over billions of years. In contrast, filaments are elongated, thread-like structures stretching across space, linking in galaxies and galaxy clusters in an intricate cosmic web. These filaments form the backbone of this web, composed mostly of dark matter and diffuse gas. Investigating the characteristics of filaments enables researchers to peer back in time to the conditions that prevailed in the early universe. Filaments reveal the influence of dark matter, which acts as the invisible scaffolding upon which galaxies coalesce, and they illuminate the processes that drove galaxy formation. The very existence of this cosmic network suggests that the universe follows a universal pattern governed primarily by gravitational attraction, indicating a preference for a specific kind of large-scale organization. Studying the dynamic relationship between cosmic voids and filaments also sheds critical light on the ongoing expansion of the universe. As space stretches and expands, galaxies drift apart, and the way matter is spread throughout the cosmos directly affects the rate of this expansion. Voids, being sparsely populated, expand more rapidly than the denser regions filled with galaxies, where gravitational forces exert a stronger pull, slowing expansion locally. This interplay between cosmic structures allows scientists to refine models of dark energy, the mysterious and still poorly understood phenomenon responsible for accelerating the universe's expansion. The complex interaction of voids and filaments carries broader implications for understanding cosmic evolution itself. By observing how galaxies cluster together or avoid certain regions, astronomers gain insight into their formation and interaction over time. These patterns raise profound questions about the fundamental nature of matter and energy, highlighting the deep allure of cosmology as a field that strives to unravel the universe's most profound mysteries. Among the most groundbreaking recent advances in cosmology is the study of gravitational waves, ripples in the fabric of spacetime generated by some of the universe's most violent and energetic phenomena. These waves arise when massive objects such as black holes or neutron stars collide or merge, sending disturbances that propagate outward at the speed of light. Albert Einstein first predicted the existence of gravitational waves over a century ago in his general theory of relativity, which describes how massive objects warp the geometry of spacetime around them. When such massive bodies accelerate, they produce gravitational waves carrying information about their origins and the nature of their violent interactions. The first ever direct detection of gravitational waves marked a monumental milestone in physics and astronomy. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, captured these elusive signals. This discovery represented an extraordinary breakthrough, proving Einstein's century-old prediction and opening an entirely new window onto the cosmos. LIGO's remarkable technology employs ultra-precise laser interferometry to measure minuscule changes in distance caused by passing gravitational waves. As these waves ripple through spacetime, they stretch and compress it, slightly altering the distances between test masses located kilometers apart. These fleeting changes are so subtle they would otherwise be undetectable, yet LIGO's sensitive instruments successfully recorded these cosmic ripples. The particular event detected by LIGO was the merger of two black holes roughly 1.3 billion light-years away from Earth. As the black holes spiraled closer and finally collided, they generated gravitational waves that propagated across space-time and reached Earth. Though the signal lasted only a fraction of a second, its power and clarity confirmed the profound impact such waves have on the fabric of the universe. This discovery has since revolutionized our understanding of black holes, neutron stars, and the extreme physics governing their interactions. With gravitational wave astronomy now a reality, scientists have gained a powerful new tool to observe phenomena invisible to traditional telescopes. This emerging field promises to deepen our knowledge of cosmic events, from cataclysmic mergers to the subtle vibrations of space-time itself, illuminating the hidden corners of the universe and continuing the quest to unlock the deepest cosmic secrets. Furthermore, this breakthrough marks the dawn of gravitational wave astronomy, opening an unprecedented window into the universe's most mysterious and energetic phenomena. Unlike traditional astronomy, which relies heavily on electromagnetic signals like visible light, radio waves, or X-rays, gravitational waves offer a revolutionary way to observe the cosmos. They provide a direct line to cataclysmic events, carrying crucial information about the violent dynamics that produce them, details that often remain hidden from conventional observation methods. One of the most remarkable features of gravitational waves is their ability to travel through dense cosmic environments without being blocked or scattered. While clouds of gas, dust, or other matter can obscure or distort light signals, gravitational waves pass through these obstacles almost unaffected. For example, when two black holes or neutron stars collide, the gravitational waves they emit ripple across the fabric of spacetime and journey through the universe unimpeded. This means scientists can detect events that are otherwise invisible through electromagnetic telescopes, giving us a rare glimpse into the universe's most extreme processes. Moreover, gravitational wave detection complements traditional astronomy by revealing aspects of cosmic phenomena that electromagnetic observations alone cannot capture. A striking example occurred when scientists observed the merger of two neutron stars. In this historic event, detectors not only picked up gravitational waves, but also detected electromagnetic radiation emitted during the collision. This multi-messenger approach allowed researchers to piece together a more complete picture of the event, leading to groundbreaking insights such as understanding how heavy elements like gold and platinum are formed in the cosmos. As gravitational wave astronomy advances, it promises to revolutionize our knowledge of the universe's most elusive and energetic phenomena. By capturing and analyzing these ripples in spacetime, scientists deepen their understanding of fundamental cosmic mysteries, from the nature of black holes and neutron stars to the very laws of gravity. This new frontier challenges and expands our comprehension of the universe's structure, its evolution, and the forces shaping it. Several cosmic events are known to generate gravitational waves strong enough to be detected here on Earth, especially those involving massive objects accelerating at incredible speeds. Among the most significant are black hole mergers. When two black holes spiral closer together, their intense gravitational fields create powerful disturbances in spacetime. As they collide and merge, these ripples, gravitational waves, spread outward, eventually reaching observatories such as LIGO and Virgo, which have been instrumental in detecting these signals. Neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, also produce detectable gravitational waves when they merge. These collisions unleash enormous energy, generating waves that ripple through space-time. These events are particularly valuable for study because they often emit electromagnetic signals alongside gravitational waves, enabling scientists to observe the same event through multiple channels. This dual observation enhances the depth and breadth of our understanding. Even more exotic collisions, such as those between black holes and neutron stars, produce gravitational waves with unique signatures. The dynamics of these extreme interactions provide vital clues about the properties of these compact objects, including their masses, spins, and internal structures. Studying these systems helps scientists probe the nature of matter under the most extreme conditions, offering invaluable insights into fundamental physics that cannot be replicated on Earth. In essence, gravitational wave astronomy represents a profound leap forward in humanity's quest to unravel the cosmos. By listening to the ripples in space-time created by these extraordinary events, we open new doors to understanding the universe's hidden stories, reshaping our perspective on the forces that govern all matter and energy. Furthermore, other fascinating phenomena, such as the rapid rotation of highly asymmetric supernova explosions, can produce gravitational waves. These signals, however, often present significant challenges for detection due to their complex and subtle nature. Yet, the ever-growing field of gravitational wave astronomy is pushing the boundaries of our understanding, unveiling cosmic events that have remained invisible to traditional telescopes and electromagnetic observations. As technology advances and observational techniques become more refined, the catalog of detectable cosmic phenomena is expected to grow dramatically, opening new windows into the universe's most enigmatic occurrences. Gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, operate on a sophisticated technique called interferometry. These detectors use highly sensitive instruments designed to measure incredibly tiny changes in distance caused by gravitational waves passing through space-time. LIGO's design features two long arms arranged in an L shape, each stretching several kilometers. Powerful laser beams are split and sent down these arms, bouncing off mirrors positioned at their far ends. When a gravitational wave sweeps through the detector, it distorts space-time just enough to alter the distance the laser beams travel. One arm might stretch slightly while the other contracts, changing the time it takes for the light to travel back and forth. The variations LIGO measures are unimaginably small, on the order of 1,000th the diameter of a proton. To capture and analyze these minuscule shifts, the system uses interferometry. When the two laser beams return to their origin, they recombine and create an interference pattern. This pattern is extremely sensitive to even the slightest differences in the paths of the beams, enabling scientists to detect the presence of gravitational waves. By examining these interference patterns, researchers can deduce the properties of the waves and, by extension, the nature of the distant cosmic events that generated them. Advanced technologies play a vital role in enhancing the sensitivity of gravitational wave detectors. State-of-the-art equipment, including ultra-stable mirrors and high-power lasers, allows scientists to detect signals so faint they would otherwise be drowned out by background noise. Environmental noise reduction techniques are equally critical. For example, suspending mirrors in a vacuum helps eliminate interference from vibrations or air currents. These innovations ensure that only genuine gravitational wave signals are observed, free from distortions caused by terrestrial disturbances. As these technologies continue to evolve, the capabilities of gravitational wave detectors will expand, offering an even deeper glimpse into the fabric of the cosmos. Since the first historic detection of gravitational waves in 2015, the field has revolutionized our understanding of the universe's most extreme phenomena. Scientists have confirmed the existence of binary black hole mergers, cosmic collisions between pairs of black holes spiraling into one another. These discoveries revealed a diverse population of black holes, many with surprising masses and spins, challenging earlier models of black hole formation and evolution. Such findings provide crucial insights into the life cycles of stars and the complex processes that govern stellar evolution. The detection of gravitational waves from neutron star mergers has been especially groundbreaking. In 2017, the merger of two neutron stars produced a gravitational wave signal accompanied by electromagnetic radiation observed across the spectrum, from gamma rays to radio waves. This multimodal observation gave astronomers an unprecedented view into the event, shedding light on the creation of heavy elements like gold and platinum, elements whose cosmic origins had long puzzled scientists. This discovery advanced our knowledge of nucleosynthesis, the cosmic process by which elements are forged, enriching our understanding of how the building blocks of matter came to be. Beyond studying individual cosmic events, gravitational wave astronomy is pushing the frontiers of fundamental physics. The ultra-precise measurements offered by detectors like LIGO allow researchers to test the predictions of Einstein's general relativity under conditions of extreme gravity, conditions impossible to replicate on Earth. Any deviations from expected results could point toward new physics, hinting at unknown phenomena or even guiding the search for elusive mysteries, such as dark matter. In essence, the study of gravitational waves is opening unprecedented avenues for exploring the fundamental properties of space-time itself, along with the forces that govern our universe. This new form of astronomy is revealing a universe once hidden from view, offering us a powerful tool to understand the most violent and mysterious cosmic events and deepening our grasp of the laws that shape reality. Additionally, the advent of gravitational wave observations is revolutionizing astronomy in unprecedented ways. As scientists continue to detect and study these ripples in the fabric of space-time, a brand new branch of astronomy, gravitational wave astronomy, is rapidly taking shape. This exciting field opens a unique window into the universe, allowing researchers to explore cosmic phenomena that were previously invisible through traditional means like light or radio waves. With every new gravitational wave discovery, we gain profound insights into some of the most violent and energetic events in the cosmos, such as merging black holes and neutron star collisions. These groundbreaking findings promise to reshape our understanding of the fundamental workings of the universe and will undoubtedly lead to even more astonishing revelations in the coming years. Cosmic rays, on the other hand, are another fascinating aspect of high-energy astrophysics. These particles are tiny but incredibly powerful travelers, speeding through space at nearly the speed of light. Mostly made up of protons, cosmic rays also include heavier atomic nuclei, electrons, and various subatomic particles. When these cosmic visitors slam into Earth's atmosphere, they trigger a complex chain reaction. Collisions with atmospheric atoms and molecules produce cascades of secondary particles, which can be detected by instruments on the ground or satellites orbiting Earth. The origins of cosmic rays have long puzzled scientists, with ongoing research revealing that many originate within our own galaxy, the Milky Way. Supernova, catastrophic explosions marking the death of massive stars, are among the primary sources of cosmic rays in our galaxy. These stellar deaths unleash shock waves that accelerate particles to astonishing speeds, creating ideal conditions for producing cosmic rays. Additionally, pulsars, which are rapidly spinning neutron stars emitting beams of radiation, play a vital role. Their intense magnetic fields can accelerate particles to extreme energies, contributing further to the cosmic ray population. Beyond the Milky Way, some of the most energetic cosmic rays likely come from active galactic nuclei. These regions, surrounding supermassive black holes at the centers of distant galaxies, can accelerate and eject matter at nearly the speed of light, producing high-energy particles. Gamma-ray bursts, which are among the universe's most powerful explosions, are also suspected sources of these cosmic rays. Studying cosmic rays is crucial for multiple reasons. Not only do they help deepen our understanding of particle physics and the energetic processes shaping our universe, but they also present challenges for life on Earth. While Earth's magnetic field provides a strong shield, protecting us from many cosmic rays, some high-energy particles still penetrate the atmosphere and reach the surface. This interaction raises important questions about their effects on human health and technology. Ongoing scientific investigations aim to clarify the origins of cosmic rays and assess their broader implications, which include both the natural environment and living organisms. When cosmic rays collide with Earth's atmosphere, they cause significant and wide-ranging effects. These high-energy particles smash into atomic nuclei, sparking a cascade of secondary particles such as muons, pions, and other charged particles. Some of these secondary particles penetrate deep into the atmosphere, with a few even reaching the ground. This particle shower influences atmospheric chemistry and biological systems alike. For example, cosmic rays contribute to atmospheric ionization, an essential process that produces ions, which in turn play a role in cloud formation and weather dynamics. This ionization is part of the natural background radiation on Earth and assists in the creation of cloud condensation nuclei, tiny particles on which water vapor condenses to form clouds. Some scientists are exploring whether fluctuations in cosmic ray intensity might correlate with climate changes, though this remains a debated and ongoing area of research. Biologically, cosmic rays pose potential risks. Even with Earth's protective atmosphere and magnetic shield, some particles penetrate and ionize cells and genetic material. This radiation exposure has been linked to increased risks of DNA damage and cancer. People with greater exposure to cosmic rays, such as astronauts in space and airline pilots flying at high altitudes, are monitored carefully for radiation effects. Understanding these risks is critical as humanity pushes further into space and continues to grapple with cosmic rays' subtle but significant impact on life and technology here on Earth. In sum, both gravitational waves and cosmic rays offer scientists remarkable opportunities to probe the universe's most energetic and mysterious phenomena. Through relentless observation and analysis, researchers are peeling back the layers of the cosmos, uncovering secrets that stretch from the smallest particles to the largest cosmic collisions, forever expanding our view of the universe and our place within it. Cosmic rays, invisible yet relentless, traverse the vastness of space, impacting not only our planet but also the delicate technology we rely on daily. These high-energy particles, traveling at near light speeds, have profound effects on modern technological systems. When cosmic rays penetrate Earth's atmosphere, they don't just pass harmlessly through, they can disrupt the very electronics that power satellites and aircraft communication systems, especially those operating at high altitudes. This interference manifests as transient glitches known as single-event upsets, where bits of computer memory flip unexpectedly, causing errors or malfunctions. In more severe cases, cosmic rays can physically damage sensitive components, risking the failure of critical systems. As society's dependence on technology grows, especially in fields like aerospace, telecommunications, and navigation, understanding these cosmic intruders and developing strategies to shield our devices becomes vital for maintaining safety and reliability. But cosmic rays are only one part of the universe's energetic drama. Among the most awe-inspiring phenomena observed are gamma-ray bursts, extraordinary explosions that release energy in a flash so intense it outshines entire galaxies. These bursts emit powerful gamma radiation, the most energetic form of light, lasting anywhere from a fraction of a second to several hours. To put it into perspective, a single gamma-ray burst can release more energy in just a few seconds than our sun will emit during its entire 10 billion-year lifetime. These brief yet violent cosmic events, often originating billions of light years away, have captivated astrophysicists seeking to unlock the secrets of the high-energy universe. Scientists classify gamma-ray bursts into two main types: long-duration and short-duration bursts. Long-duration bursts, those lasting longer than about 2 seconds, are thought to result from the death throes of massive stars. When such a star runs out of nuclear fuel, it collapses catastrophically, triggering a supernova explosion and forming either a neutron star or a black hole. In this process, highly focused jets of particles move at nearly the speed of light, producing the intense gamma radiation that defines these bursts. On the other hand, short-duration bursts, lasting less than 2 seconds, likely originate from the collision of compact objects like neutron stars or black holes. When two neutron stars spiral inward and merge, the violent event unleashes a torrent of energy, including gamma rays. This theory gained strong support in 2017 when scientists observed both gravitational waves and electromagnetic radiation from a neutron star merger, a landmark moment that connected these cosmic fireworks with the ripples in space-time itself. Studying gamma-ray bursts offers more than just understanding spectacular explosions. It provides a window into the most extreme environments in the universe. The incredible energies involved reveal clues about how stars evolve, how matter behaves under intense gravity, and how heavy elements like gold and platinum are formed. Many of these bursts come from distant regions where stars are actively forming, allowing astronomers to peer back into the early universe and gain insight into the processes that shaped galaxies over billions of years. To detect and analyze these cosmic phenomena, scientists rely on an array of sophisticated instruments both on the ground and in space. One area of active research involves ultra-high energy cosmic rays, particles that carry energies exceeding 1 billion electron volts, far surpassing typical cosmic ray energies. These particles are extremely rare, making their detection a formidable challenge that demands international collaboration and cutting-edge technology. Ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in the United States employ a technique called extensive air shower detection. When an ultra-high energy cosmic ray smashes into molecules in Earth's atmosphere, it triggers a cascade of secondary particles spreading over large areas, known as an air shower. Arrays of detectors capture these showers, allowing scientists to deduce the original particle's energy and composition by analyzing the shower's density and spread. Complementing these efforts are space-based instruments such as the Alpha Magnetic Spectrometer aboard the International Space Station and the Cosmic Ray Observatory, which provide direct measurements of cosmic rays outside the atmosphere. These missions help determine the charge, momentum, and energy of cosmic rays, offering a fuller picture of their origins and behavior. Alongside observational techniques, theoretical models and simulations are crucial for interpreting the data. Researchers aim to identify the cosmic sources responsible for these powerful particles, whether they be remnants of supernovae, active galactic nuclei powered by supermassive black holes, or other exotic astrophysical phenomena. As detection technologies and data analysis methods continue to advance, scientists are steadily peeling back the layers of mystery surrounding ultra-high energy cosmic rays, revealing new insights about the universe's most violent and energetic processes. Cosmic rays serve as messengers from the furthest reaches and most intense corners of the cosmos, carrying with them vital information about astrophysical events too extreme to replicate on Earth. Their varied composition, ranging from helium nuclei to heavier elements and even heavier nuclei, reflects the diversity of their sources and the complex acceleration mechanisms involved. By examining these elemental ratios and their energy spectra, scientists hope to trace the journey of cosmic rays back to their origins, deepening our understanding of stellar explosions, black hole environments, and the fundamental workings of the universe. Through this pursuit, humanity gains not only scientific knowledge, but also a profound connection to the energetic forces shaping the cosmos. Moreover, cosmic rays serve as invaluable messengers, illuminating the mysterious processes of particle acceleration near some of the most powerful astrophysical phenomena in the universe. These energetic particles reach energies that far exceed those produced by even the most advanced human-made particle accelerators, offering a natural laboratory for scientists to explore how such incredible forces come into play. By observing cosmic rays, researchers gain crucial insights into how particles achieve these ultra-high energies, often reaching levels that challenge our current understanding of physics. Unraveling the mechanisms behind particle acceleration not only sheds light on the extreme environments where matter and radiation interact, but also pushes the boundaries of fundamental physics. These processes occur in cosmic settings so extreme, such as supernova remnants, active galactic nuclei, and gamma-ray bursts, that they provide a window into conditions unattainable on Earth. Through detailed study of cosmic rays, scientists can explore how energy is transferred, transformed, and propagated across vast distances, deepening our comprehension of the universe's most energetic events. Another critical role cosmic rays play is in probing the interstellar medium, the vast, diffuse material that fills the space between stars within galaxies. As cosmic rays journey through this interstellar environment, they ionize gases and alter the chemical composition of the medium, influencing the physical conditions between stars. This interaction provides astrophysicists with a powerful tool to investigate how cosmic rays move through space, the ways in which they transport energy and momentum, and how they impact star formation processes. By affecting the density and temperature of interstellar clouds, cosmic rays help regulate the birth of new stars, linking these high-energy particles directly to the ongoing evolution of galaxies. In this way, cosmic rays are not only markers of extreme cosmic events, but also key players in the grander tapestry of the cosmos. They reveal the interconnectedness of different astrophysical processes and contribute essential pieces to the puzzle of how the universe functions on both the smallest and largest scales. Expanding beyond the realm of cosmic rays, the multiverse hypothesis invites us to consider an even more profound cosmic reality. This bold idea suggests that our universe may be just one among countless others, perhaps an infinite number, existing simultaneously. Depending on which version of the multiverse theory is considered, these other universes might have entirely different physical laws, constants, and dimensions, resulting in wildly diverse realities beyond anything we experience. This concept fundamentally challenges the traditional notion of a single, self-contained universe and has captured the imagination of both scientists and philosophers alike, who debate what reality truly means. Several theoretical frameworks support the multiverse idea, each coming from different branches of physics. One of the most influential comes from cosmology and the theory of cosmic inflation. According to this theory, in the earliest moments after the Big Bang, the universe underwent a brief but incredibly rapid expansion, smoothing out irregularities and creating the uniform, flat cosmos we observe today. However, this inflationary process might not have ended everywhere at once. Instead, it could still be occurring in separate regions of space, generating bubbles or pockets of space-time that evolve into individual universes, each with its own unique physical properties. This concept is known as the inflationary multiverse. Another striking viewpoint arises from quantum mechanics, specifically the many worlds interpretation proposed by physicist Hugh Everett III in the 1950s. Quantum mechanics reveals that particles exist in superpositions, holding multiple states simultaneously until measured. Traditionally, it was believed that the act of measurement collapses this superposition into a single outcome. However, the many worlds interpretation suggests something far stranger. Instead of collapsing, all possible outcomes actually occur, but each in its own branching, parallel universe. For example, in the famous double-slit experiment, rather than the photon choosing one path, it effectively travels through both slits simultaneously, creating distinct realities for each possible outcome. This branching isn't limited to simple experiments. It extends to every quantum event, from the behavior of subatomic particles to everyday decisions. According to this view, every choice you make could spawn an entirely new universe where the alternative outcome unfolds, resulting in an unimaginably vast and complex web of parallel realities. In this framework, infinite versions of you might exist, living out every possible scenario. Though the many worlds interpretation offers fascinating implications for how reality might be structured, it also raises profound questions. What does existence mean when there are countless versions of ourselves? How can we, confined to our own universe, ever verify the existence of these parallel worlds? So far, no empirical evidence has definitively confirmed or disproved this theory, leaving it in the realm of captivating speculation. Meanwhile, the inflationary multiverse offers a cosmological counterpart, suggesting that the cosmos is not a single entity but a vast ensemble of universes born from the same fundamental process of rapid expansion. Cosmic inflation was initially proposed to solve puzzling features of our universe, like its remarkable uniformity and the large-scale distribution of galaxies. The idea is that this rapid growth smoothed out any irregularities, producing a homogeneous and isotropic universe. If inflation continues in some regions of space, it could give rise to countless bubble universes, each with different physical laws and constants. This raises exciting possibilities about the fine-tuning observed in our own universe, where conditions appear just right to support life. The multiverse hypothesis might explain why our universe has these life-friendly properties. As just one of many, it happens to be the one capable of supporting observers like us. Despite its allure, the multiverse concept remains deeply speculative. Current scientific tools and observations have yet to provide concrete evidence for the existence of these other universes, and the hypothesis continues to fuel lively debate within the scientific community. Together, these ideas, cosmic rays as probes of extreme physics and the multiverse as a framework for understanding reality, push the boundaries of human knowledge. They invite us to explore questions about the nature of existence, the structure of the cosmos, and our place within it, encouraging a never-ending quest to comprehend the universe in all its staggering complexity. However, the inflationary multiverse theory takes the idea of cosmic inflation far beyond a single explosive event at the birth of our universe. Instead, it envisions inflation as a never-ending, dynamic process unfolding across an immense, all-encompassing fabric of space-time. Within this grand cosmic arena, countless bubble universes are constantly forming. Each bubble springs into existence when a region of space rapidly expands, an event known as inflation, and then eventually slows down, creating a distinct universe with its own unique physical laws and properties. Imagine one bubble universe where the familiar constants and forces govern everything as we know them. Gravity, electromagnetism, and nuclear forces behave in a way that supports galaxies, stars, planets, and ultimately, life. Now picture another bubble universe, born under entirely different conditions. Its physical constants could be wildly different, allowing exotic forms of matter or even unfamiliar fundamental forces to dominate. This endless diversity of universes might provide the key to a puzzling mystery, the remarkable fine-tuning we observe in our own universe, where the precise values of constants seem perfectly set to allow life to emerge. The inflationary multiverse theory suggests we happen to live in one of those rare bubbles where conditions align just right for life to flourish. One of the most profound implications of this theory is how it reshapes our understanding of why the universe has the parameters it does. Rather than assuming our universe is a singular, unique entity finely calibrated by some external mechanism, the multiverse model proposes that countless universes exist with a staggering variety of configurations. We simply find ourselves in one whose parameters are just so, a cosmic coincidence made possible by the sheer number of universes in existence. This perspective reframes long-standing questions about cosmic design and the anthropic principle, offering a natural explanation for why the cosmos looks so hospitable to life. Yet, despite its captivating elegance, the inflationary multiverse theory remains highly speculative and difficult to test with current scientific tools. Empirical validation is a major challenge, as, by definition, other universes lie beyond our observable horizon, like unreachable with direct measurement. Still, physicists are diligently exploring indirect methods to probe the theory's validity. These efforts focus on searching for subtle fingerprints or anomalies in our own universe that might betray the influence or existence of other bubble universes. One promising avenue involves the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the universe. Researchers hypothesize that if our bubble universe has ever collided or interacted with a neighboring bubble, such encounters might leave behind telltale irregularities in this ancient radiation. These could appear as unusual temperature fluctuations or unexpected alignments in the cosmic background, patterns that deviate from what standard cosmology predicts. Detecting such signatures would be a groundbreaking clue pointing toward a multiversal reality. Another key focus centers on the puzzle of fine-tuning itself. The physical constants and laws governing our universe appear meticulously balanced to support life, a fact that has perplexed scientists and philosophers alike. The multiverse framework offers a statistical explanation. Among an immense ensemble of universes, only a tiny fraction would have the right conditions for life. By studying whether certain constants can vary across different cosmic regions, or if variations align with theoretical predictions, scientists may find indirect evidence supporting multiple universes. Advances in particle physics further complement this quest. Experiments conducted in high-energy particle colliders, such as the Large Hadron Collider, probe the fundamental nature of matter and forces at unprecedented scales. Theories like string theory predict the existence of additional dimensions and a landscape of possible universes with different physical laws. Discovering experimental signs consistent with these models could lend weight to the multiverse concept, connecting cosmic phenomena to the microscopic world. In summary, the inflationary multiverse theory offers a breathtaking vision of reality, a vast, ever-growing mosaic of universes, each with its own unique story. While the road to concrete proof is steep and uncertain, ongoing scientific exploration is gradually unveiling clues that may one day confirm or refute this extraordinary idea. In doing so, it challenges us to rethink our place in the cosmos, expanding the boundaries of what is known and what might be possible. Lastly, while direct experimental proof remains just out of reach, the ongoing breakthroughs in astrophysics, cosmology, and quantum mechanics are paving new pathways toward understanding the elusive multiverse concept. As our grasp of the cosmos deepens, scientists are relentlessly pushing boundaries, exploring intricate theories that might one day unlock new observational tools or innovative predictions. These advancements could enable us to gather evidence that either supports or challenges the multiverse hypothesis, a notion that radically shifts how we perceive reality itself. The idea of a multiverse suggests that our known universe is merely one among countless others, each governed by its own unique laws of physics and fundamental properties. This profound concept forces us to rethink the foundations of science, raising pivotal questions. Why does our universe exhibit such precise conditions that allow life to flourish? Are these conditions a mere cosmic coincidence, or is there an underlying principle that shapes all universes within this grand ensemble? If multiple universes truly exist, this challenges the assumption that the laws of physics are absolute and universal, opening the door to a staggering diversity beyond our imagination. One of the most striking implications of the multiverse theory is that physical constants, like the strength of gravity or the speed of light, might vary drastically from one universe to another. Such variations could give rise to entirely different forms of matter, energy, and perhaps even life, diverging so much from what we know that our very concepts of existence would need to expand. This possibility stretches scientific inquiry far beyond our familiar cosmic neighborhood, demanding new theoretical frameworks and mathematical models to navigate and comprehend the vastness and variety of the wider cosmos. Beyond science, the multiverse hypothesis stirs deep philosophical reflection on the nature of reality and humanity's place within it. If an infinite number of universes exist, each representing different outcomes and realities, the uniqueness of our own universe becomes uncertain. Are the laws we hold sacred truly universal, or merely local rules shaped by our particular cosmic patch? This perspective can unsettle ideas about determinism and predictability, hinting that what we observe might be just one variation among countless possibilities, an ocean of realities where the story of existence unfolds in many ways. Embracing the multiverse idea doesn't just stretch our imagination, it propels theoretical physics forward, inspiring scientists to devise novel experiments and technologies aimed at probing connections between universes. Though still speculative, this line of inquiry enriches scientific dialogue, inviting unforeseen discoveries and expanding the horizon of what we can hope to understand about existence itself. Turning to a cornerstone of modern physics, Albert Einstein's theory of general relativity transformed how we understand gravity. Instead of viewing gravity as a simple, invisible force pulling objects together, Einstein revealed it as the curvature of a four-dimensional fabric known as space-time, shaped by mass and energy. Imagine space and time not as separate entities, but woven into a single continuum where massive objects like stars and planets cause dents and curves. Smaller objects follow these curves naturally, which we perceive as gravitational attraction. This revolutionary concept contrasts sharply with Isaac Newton's classical idea of gravity as a mysterious pull between masses. Einstein's insight explains why planets orbit stars and why light bends as it passes near massive bodies, a phenomenon called gravitational lensing. His field equations describe how the presence of mass and energy warps the geometry of space-time. The heavier the object, the more dramatic the curvature. Picture a trampoline stretched tight, and when a heavy bowling ball is placed in the center, it sinks, creating a dip. Smaller balls rolling nearby will spiral inward, drawn not by force, but by the altered shape of the trampoline surface. This analogy beautifully captures the essence of gravity in Einstein's framework. General relativity's implications reach far beyond our solar system. The theory predicts extraordinary phenomena like black holes, regions where space-time is curved so steeply that nothing, not even light, can escape their grip. It also provides the foundation for understanding the expanding universe and the complex dance of galaxies. Gravity, through this lens, is no longer a static force, but a dynamic interplay between matter and the very fabric of space-time. Space-time itself is a groundbreaking concept that unifies the three dimensions of space with time into one seamless four-dimensional continuum. This view changes how we describe events. Their meaning depends not only on where they occur, but also when. Mass and energy cause distortions in this fabric, dictating how objects move and interact. The greater the mass, the deeper the curve, altering trajectories and giving rise to the gravitational phenomena we observe. Moreover, space-time is not static. Dynamic changes, such as accelerating masses or shifting energy fields, send ripples through it, gravitational waves that travel at the speed of light. These waves, detected only recently, carry information about cataclysmic cosmic events like colliding black holes, offering unprecedented insight into the relationship between matter, energy, and the structure of the universe. Testing general relativity requires diverse approaches, from precise measurements within our solar system to observations of distant stars and galaxies. Each experiment that confirms its predictions strengthens our confidence in this elegant theory, which continues to guide our exploration of the universe's most profound mysteries. One of the most remarkable moments in the history of physics took place during a solar eclipse in 1917, when scientists witnessed a groundbreaking phenomenon that would forever change our understanding of the universe. As the moon momentarily blocked the sun's bright light, astronomers seized the rare opportunity to observe the positions of stars located very close to the sun's edge. What they found was astonishing. The light from these stars appeared to bend, shifting their apparent positions in the sky. This bending of light, now known as gravitational lensing, had been predicted years earlier by Albert Einstein's revolutionary theory of general relativity. Einstein proposed massive objects like stars and planets don't simply exert a force across space. Instead, they curve the very fabric of space and time around them. When light passes near such massive bodies, it follows the curved paths within this warped space-time, causing the apparent shift in star positions observed during the eclipse. The measurements taken confirmed that Einstein's theory was not just an abstract mathematical idea, but a real description of how gravity works in our universe. This moment was one of the first powerful confirmations that space and time are intertwined and can be distorted by mass. Another critical test of general relativity comes from careful observations of the motions of planets and moons within our own solar system. The orbits of planets aren't perfect ellipses. They slowly shift or precess over time. Mercury, the innermost planet, exhibits this effect more prominently than others. Scientists discovered that Mercury's orbit advances slightly with each revolution in a way that Newtonian physics, the classical theory of gravity, could not fully explain. General relativity, however, predicted this additional shift precisely. The theory showed that the intense gravitational field near the Sun warps space-time in such a way that Mercury's orbit naturally precesses, confirming the theory's predictive power in our cosmic backyard. But the story doesn't end there. The 21st century brought some of the most thrilling confirmations of Einstein's ideas with a direct detection of gravitational waves, ripples in space-time itself. These waves were first observed by the Laser Interferometer Gravitational Wave Observatory, or LIGO, in 2015. These faint tremors were generated by cataclysmic cosmic events such as the collision and merger of two black holes or neutron stars. The waves stretched and squeezed space-time as they passed through Earth, and their properties perfectly matched predictions made by general relativity. For the first time, scientists were able to listen to the universe in a completely new way, opening a fresh window onto the most violent and energetic processes in the cosmos. Further proof of general relativity's profound insights comes from experiments involving atomic clocks. By comparing highly precise clocks placed on satellites orbiting Earth with those on the planet's surface, scientists demonstrated a fascinating effect called gravitational time dilation. According to Einstein's theory, time itself runs at different rates depending on the strength of gravity. Clocks closer to massive bodies, where gravity is stronger, tick more slowly than those further away. This subtle but measurable difference has important real-world implications. For example, the clocks on GPS satellites must be continually corrected for both their high speeds and weaker gravitational pull relative to clocks on Earth to maintain the pinpoint accuracy of global positioning systems we rely on every day. One of the most mysterious and extreme predictions of general relativity is the existence of singularities, points in spacetime where gravitational forces become infinitely strong and our known laws of physics break down. At these singularities, quantities such as density and curvature of spacetime are theorized to reach unimaginable values that defy our current ability to compute or understand. The most famous singularities lie at the centers of black holes, where matter is thought to be crushed into an infinitely small, infinitely dense point. Black holes are surrounded by a boundary called the event horizon, beyond which nothing, no matter, no light, can escape the black hole's overwhelming gravitational grip. This creates a region of space-time completely cut off from the rest of the universe. Once anything crosses this boundary, it is lost to the outside world forever. Inside this realm, the equations of general relativity no longer offer clear answers, signaling a profound gap in our understanding of physics. Singularities may also have played a role at the very birth of the universe itself. The leading cosmological models suggest that the universe began in a state of incredibly high density and temperature, compressed into an infinitely small volume, a primordial singularity known as the Big Bang. These extreme conditions challenge physicists to reconcile general relativity with quantum mechanics, the theory governing the subatomic world. This quest drives efforts to develop a unified theory of quantum gravity, which could describe nature's laws consistently across both the cosmic and quantum scales. While singularities remain theoretical constructs emerging from our current gravitational models, they highlight the limits of those models under extreme conditions. As researchers push forward with theories like string theory and quantum gravity, they hope to shed light on these enigmatic points, potentially unlocking secrets about the fundamental nature of space, time, and matter itself. Each new discovery could revolutionize our understanding of how the cosmos functions, from its vastest expanses to its tiniest constituents. Time dilation itself is one of the most fascinating consequences of Einstein's theories of relativity. It reveals that time is not absolute or fixed, but instead varies depending on how fast observers move relative to each other or their position within a gravitational field. There are two main types of time dilation. The first, special relativistic time dilation, arises when objects move at high speeds. The closer an object's speed approaches the speed of light, the slower time passes for that object relative to a stationary observer. This concept can be illustrated with the famous twin paradox. If one twin travels through space at nearly the speed of light while the other remains on Earth, the traveling twin ages more slowly and returns younger. The second type, gravitational time dilation, occurs due to differences in gravitational strength. According to general relativity, clocks situated closer to massive objects where gravity is stronger run more slowly compared to clocks farther away. This phenomenon is not just theoretical, it's directly observed in real-world systems like the GPS network. Satellites orbiting high above Earth's surface experience both less gravitational pull and move at high speeds, so engineers must adjust their clocks to compensate for the combined effects of special and gravitational time dilation. Without these corrections, GPS positioning would quickly become inaccurate, highlighting the practical impact of Einstein's profound insights into time and space. Through these groundbreaking experiments and observations, from the bending of starlight during a solar eclipse to the detection of gravitational waves, from planetary orbits to atomic clocks, scientists continue to test and validate the extraordinary predictions of general relativity. Each step deepens our understanding of the universe's fundamental workings and reveals the astonishing ways gravity shapes the cosmos, guiding the grand dance of planets, stars, galaxies, and even time itself. Additionally, groundbreaking experiments using particle accelerators have provided compelling confirmation of time dilation, a phenomenon predicted by Einstein's theory of relativity. Scientists have studied particles known as muons, unstable subatomic particles, by accelerating them to speeds approaching that of light. At these incredible velocities, the muons' decay times stretch noticeably when observed from a stationary frame of reference. This striking difference in decay duration offers direct, tangible evidence of time dilation, validating the profound idea that time itself is not absolute, but can stretch and contract depending on relative motion. This insight deepens our grasp of the fabric of time and how it operates within the universe. Turning to the microscopic world, quantum mechanics emerges as a crucial framework for understanding the universe at its most fundamental level. Unlike classical physics, which falls short when explaining the strange behavior of particles smaller than atoms, quantum mechanics reveals a realm where matter and energy behave in ways that defy everyday intuition. This theory captures the interactions of subatomic particles and energy, shedding light on phenomena impossible to comprehend through classical means. Through the lens of quantum mechanics, scientists uncover the fundamental building blocks of reality and gain valuable perspectives on cosmic processes that shape the universe on the grandest scales. One of the most profound applications of quantum mechanics is in cosmology, the study of the universe's origins and evolution. Moments after the Big Bang, the cosmos was unimaginably hot and dense, dominated by quantum effects. Tiny quantum fluctuations during this infancy of the universe acted as seeds, eventually growing into the massive structures we observe today. Galaxies, clusters, and vast cosmic webs. This interplay between quantum behavior and cosmic evolution reveals that the universe's large-scale architecture is deeply rooted in quantum processes, highlighting a remarkable connection between the smallest and largest scales in existence. Quantum mechanics also challenges our understanding of black holes, those mysterious regions where gravity is so intense that not even light can escape. According to quantum theory, particles can exist in multiple states simultaneously, a concept known as superposition, and become mysteriously linked through entanglement. These properties defy the classical views of black holes, giving rise to perplexing puzzles like the black hole information paradox. This paradox stems from conflicting principles. General relativity predicts that information entering a black hole might be lost forever, while quantum mechanics insists that information must be preserved. Resolving this paradox is one of the most profound challenges at the crossroads of quantum mechanics and gravitational physics. Expanding this union further, quantum field theory merges quantum mechanics with special relativity to describe fundamental forces such as electromagnetism and the weak and strong nuclear forces. This sophisticated framework underpins the standard model of particle physics, which catalogs all known particles and their interactions. As researchers push the boundaries of our knowledge about the universe's origins and its fundamental nature, quantum mechanics continues to drive theoretical advancements and guides investigations into some of the greatest cosmic mysteries: dark matter, dark energy, and the quest for a unified theory that reconciles all forces of nature. Among the most fascinating phenomena in quantum mechanics is quantum entanglement, where two or more particles become intertwined so that the state of one instantly influences the state of the other, no matter how far apart they are. This instantaneous connection defies the classical expectation that information can only travel at or below the speed of light. Albert Einstein famously dubbed this spooky action at a distance because it so fundamentally challenges our understanding of how the universe works. Entanglement has been demonstrated repeatedly in experiments, solidifying its role as a cornerstone of quantum theory. The implications of entanglement extend far beyond individual particles, influencing larger systems and even cosmic phenomena. For example, understanding entanglement is crucial when studying particles in extreme environments like the vicinity of black holes or during the universe's earliest moments when quantum effects reign supreme. Some theoretical models suggest that entangled states could affect the universe's expansion and the mysterious dark matter and dark energy that dominate its composition. This hints at a concept known as cosmic coherence, where quantum states remain correlated across vast distances and enormous systems like galaxies or clusters. Beyond cosmology, quantum entanglement holds transformative potential for technology. Harnessing entangled particles promises breakthroughs in quantum computing, which could revolutionize information processing and quantum communication, which offers unparalleled security. These advances could reshape computing and data transmission in profound ways. Finally, exploring quantum entanglement within the cosmos serves as a vital bridge between quantum mechanics and general relativity, the two foundational yet incompatible pillars of modern physics. While quantum mechanics describes the strange probabilistic world of the very small, general relativity governs gravity and the warping of space-time on massive scales. Reconciling these theories remains one of the greatest scientific quests, promising a deeper understanding of reality itself and unveiling new truths about the universe's most fundamental nature. However, the core principles underlying the two towering pillars of modern physics, general relativity and quantum mechanics, stand in stark contrast, presenting profound puzzles that have challenged scientists for decades. The crux of the difficulty lies in the very nature of gravity as portrayed in these frameworks. In general relativity, gravity is not simply a force but a manifestation of the curvature of space and time caused by mass and energy. Imagine space-time as a flexible fabric, bending and warping wherever massive objects reside, guiding the motion of everything within it. This geometric view contrasts sharply with the way quantum mechanics treats forces, as interactions mediated by particles, following probabilistic rules. This fundamental conceptual divide creates a barrier to formulating a single, all-encompassing theory that can describe the universe both at the colossal scales of planets and galaxies and the minuscule world of subatomic particles. Scientists have devoted enormous effort to bridging this gap. Among the most ambitious attempts is string theory, a groundbreaking framework that replaces point-like particles with tiny, vibrating one-dimensional strings. These strings vibrate at different frequencies, giving rise to the particles and forces we observe. Importantly, string theory naturally includes gravity by proposing the existence of the graviton, a hypothetical particle that carries the gravitational force. Beyond this, string theory opens the door to a bewildering landscape of possible universes, each with different physical laws and additional spatial dimensions beyond the familiar three. These extra dimensions could hold the key to reconciling the quantum and relativistic views, providing a framework in which both can coexist. Despite its elegance and promise, string theory remains largely theoretical, with major challenges in experimentally testing its predictions. Another promising direction is loop quantum gravity, which takes a different path by attempting to quantize space-time itself. This approach envisions space-time as composed of tiny, discrete loops woven into an intricate network. Rather than treating gravity as geometry alone, loop quantum gravity emphasizes the quantum properties of the very fabric of space and time. This granular structure could resolve perplexing issues such as singularities, points of infinite density found in black holes in the Big Bang, by suggesting that space-time has a smallest possible scale and cannot be infinitely compressed. While these frameworks illuminate potential paths toward unifying the laws of physics, a fully unified theory remains elusive. Researchers continue to investigate phenomena such as black holes, cosmic expansion, and the very texture of space-time, inching closer to a deeper understanding of the universe's underlying order. Their journey traverses the vast and the infinitesimal, seeking the harmony between the deterministic rules of relativity and the probabilistic nature of quantum mechanics. One concept emerging from these explorations is quantum foam. Rooted in quantum field theory, quantum foam describes the idea that at unimaginably small scales, on the order of the Planck length, which is about 100 billion trillion times smaller than a proton, space-time itself is not smooth or continuous. Instead, it froths with fluctuations and turbulence, much like the surface of a turbulent sea. This foamy structure embodies the inherent uncertainties of quantum mechanics, suggesting that space-time is dynamic and ever-changing at these minuscule scales. Within this quantum foam, particles and fleeting virtual particles pop in and out of existence in a chaotic dance, creating a seething environment that could influence physical processes on larger scales. This insight challenges the traditional view of space-time as a stable, passive backdrop. Instead, the very fabric of reality appears to be alive with quantum activity, blurring the lines between space, time, matter, and energy. The implications are profound. Fluctuations in the quantum foam could cause subtle variations in gravitational fields, affecting how gravity operates in different contexts. This relationship complicates the quest to unify quantum mechanics with general relativity, as the fabric of space-time may not behave predictably at its most fundamental level. Yet it also opens new avenues for research. Understanding the interplay between quantum foam, gravity, and energy could provide critical insights for theories like string theory and loop quantum gravity, bringing physicists closer to unveiling a coherent picture of the cosmos. Another striking phenomenon that illustrates the strange quantum world is quantum tunneling. This process allows particles to pass through energy barriers that would be insurmountable according to classical physics. Quantum tunneling plays a vital role in stellar environments, especially in the nuclear fusion reactions that power stars. In the extreme temperatures of millions of degrees inside stars, hydrogen nuclei fuse to form helium, releasing vast amounts of energy. Without quantum tunneling, these fusion reactions would be far less likely, and stars as we know them, including our own sun, would not shine. Together, these concepts, string theory, loop quantum gravity, quantum foam, and quantum tunneling, represent humanity's bold attempts to understand the universe at its most fundamental level. They reveal a reality far stranger and more intricate than everyday experience, inviting us to explore the very nature of space, time, and matter. The quest to unify these ideas continues to inspire physicists around the world, driving forward the frontier of knowledge in the search for the ultimate theory of everything. However, the journey of two positively charged protons coming together to fuse is far from straightforward. The electrostatic force between these protons creates a formidable energy barrier, a wall of repulsion that classical physics tells us only the fastest, most energetic protons could possibly overcome. This barrier, known as the Coulomb barrier, demands an enormous amount of energy for fusion to occur. At first glance, it seems only those protons moving with tremendous speed enough to break through this barrier would manage to unite. Yet nature has a remarkable trick up its sleeve: quantum tunneling. This subtle but powerful quantum phenomenon allows protons with energies lower than this barrier to still have a finite chance of tunneling through it, bypassing what classical physics would consider impossible. In other words, even slower protons can fuse because they don't have to climb over the barrier. They can slip right through it. Without this quantum effect, the fusion of hydrogen into helium, the fundamental reaction powering stars like our sun, would be drastically limited, especially at temperatures that would otherwise seem too low for such processes to proceed efficiently. Quantum tunneling is not just a curious quirk. It is a cornerstone of stellar physics. It enables stars to shine steadily by maintaining fusion reactions at temperatures and pressures far below what classical calculations would require. The rate of these nuclear reactions directly influences a star's luminosity, lifespan, and evolution. Without tunneling, stars would struggle to sustain the energy output necessary for their stability, leading to a cosmos dramatically different from the one we know. No long-lived stars, no planets warmed by their light, and no conditions ripe for life. Moreover, quantum tunneling plays a critical role beyond the fusion of hydrogen. In the fiery deaths of massive stars, supernovae, tunneling facilitates nuclear reactions that synthesize heavier elements beyond helium. These cosmic cataclysms spread these elements across the universe, seeding the raw materials for planets, life, and the chemical complexity that defines the cosmos. Thus, quantum mechanics operates not only in the microscopic realm, but extends its influence to the grandest cosmic scales, shaping the life cycles of stars and the very fabric of the universe's chemistry. Understanding quantum tunneling unveils a profound connection. The delicate dance of subatomic particles governs the colossal processes of stellar life and cosmic evolution. It is a vivid reminder that the vast universe and the tiny quantum world are deeply intertwined, each influencing the other in ways we are only beginning to comprehend. Shifting focus from the microcosm to the macrocosm, we encounter another mysterious cosmic entity, the Great Attractor. This gravitational anomaly lies deep in intergalactic space, nestled within a region called the Laniakea supercluster. Here, gravity's pull is so immense it governs the motion of entire galaxies, including our own Milky Way. Observations reveal that galaxies are not drifting aimlessly, but are collectively drawn toward this enigmatic focal point. The Great Attractor represents a colossal concentration of matter, including countless galaxies, dark matter, and possibly unknown forms of matter. Its total mass is staggering, millions of billions of times that of our Sun. Yet, despite its enormous influence, the exact nature of the Great Attractor remains shrouded in mystery. Positioned behind the dense plane of the Milky Way, it lies obscured from our direct view, complicating astronomers' efforts to unravel its secrets. Its gravitational effect is evident in the peculiar velocities of galaxies, which move not only because of the universe's expansion, but also because they are being pulled toward this hidden giant. The Milky Way, along with its neighboring galaxies, is hurtling through space toward a point in the constellation Hydra, drawn by the invisible hand of the Great Attractor. Studying this phenomenon deepens our understanding of the universe's large-scale structure. It reveals that galaxies are not scattered randomly, but are shaped and influenced by massive gravitational hubs like the Great Attractor. These discoveries suggest the cosmos is woven into a complex web of matter and gravity, a vast network where colossal structures steer the motions of countless galaxies. As technology advances and telescopes improve, astronomers continue to probe this gravitational mystery, hoping to uncover what lies behind the veil. The Great Attractor remains a key piece in the cosmic puzzle, shedding light on how mass is distributed and how the universe's vast architecture functions. Meanwhile, one of the most enigmatic cosmic phenomena discovered in recent decades is the fast radio burst, or FRB. These fleeting flashes of radio waves last only milliseconds, yet they release an astounding amount of energy, comparable to the total energy our Sun emits over several days. First detected in 2007, FRBs originate from galaxies billions of light years away, making them not only intense, but also incredibly distant and transient signals. Their brief and unpredictable nature poses a challenge for astronomers. Some FRBs appear as one-time events, while others repeat sporadically, suggesting a variety of possible sources or mechanisms. Among the leading theories is that FRBs come from magnetars, highly magnetized neutron stars, remnants of massive stars that exploded as supernovae. These stellar remnants possess magnetic fields billions of times stronger than Earth's, and sudden releases of magnetic energy, perhaps triggered by starquakes, violent shifts in their crusts, could produce these intense bursts. Other theories explore even more dramatic origins, such as the collision or merger of compact objects like neutron stars or black holes. These cataclysmic events could unleash the energy necessary for FRBs, matching observations of some repeating bursts and their complex behavior. Adding to the intrigue is a speculative notion that FRBs might be signals from advanced extraterrestrial civilizations, though this remains highly uncertain and controversial. Regardless of their origin, FRBs offer a tantalizing glimpse into extreme astrophysical processes and the dynamic universe beyond our galaxy. Scientists continue to track and analyze FRBs using powerful radio telescopes worldwide. By studying characteristics such as how the signals spread out, their polarization and timing, researchers aim to understand the cosmic environments where these bursts originate and the physics driving them. Together, these cosmic phenomena, from quantum tunneling powering stars to gravitational giants shaping galaxy motions to mysterious bursts of radio waves, paint a vivid picture of a universe rich in complexity, wonder, and ongoing discovery. Each layer reveals new mysteries, inviting us to explore further the grand tapestry of the cosmos. Ultimately, unraveling the mysteries of fast radio bursts, those intense fleeting flashes of radio waves from distant galaxies, not only challenges our most basic assumptions about the cosmos, but also opens an entirely new frontier for exploring the universe. These enigmatic bursts push scientists to reconsider what we know about neutron stars, some of the densest objects in existence, and even suggest the tantalizing possibility of phenomena that stretch beyond the limits of current physics. As investigations into fast radio bursts deepen, they have transformed into one of the most captivating puzzles in modern astrophysics, revealing cosmic events so complex and perplexing that they constantly stretch the boundaries of our understanding of space and time. Meanwhile, ultra-diffuse galaxies, often abbreviated as UDGs, represent a strikingly different yet equally mysterious chapter in the story of the universe. These ghostly galaxies are marked by their extraordinarily low surface brightness, making them incredibly difficult to detect against the cosmic backdrop. Despite this faintness, ultra-diffuse galaxies can span regions up to 10 times larger than our own Milky Way, yet contain only a tiny fraction of its mass. Their sheer size combined with their near transparency forces astronomers to rethink traditional models of galaxy formation and structure. Unlike typical galaxies bursting with stars and glowing gas, UDGs seem to have taken a more subdued and puzzling path through cosmic history. One leading theory proposes that many ultra-diffuse galaxies are the remnants of once more active galaxies, stripped of their gas and star-forming material. Such stripping occurs in dense environments like galaxy clusters, where gravitational forces from neighboring galaxies can effectively pull away the fuel needed for new stars to form. This process leaves behind a ghostly shell, a galaxy that stretches outward but lacks the brilliant starlight that usually defines such massive structures. Another intriguing possibility is that UDGs owe their existence to dark matter, the mysterious and invisible substance thought to make up most of the universe's mass. Given that ultra-diffuse galaxies seem to have an unexpectedly high proportion of dark matter relative to their visible matter, some scientists believe these galaxies are dominated by this elusive material. Dark matter's gravity could have played a crucial role, enabling clouds of gas to collapse into galaxies that never sparked the intense star formation typical of more familiar galaxies. Observations reveal that UDGs inhabit diverse cosmic neighborhoods. Some drift in isolation across vast empty spaces, while others nestle in crowded galaxy clusters. This variety hints at a complex interplay between dark matter, ordinary matter, and the environmental conditions that have shaped these galaxies over billions of years. Studying ultra-diffuse galaxies offers astronomers a valuable window into some of the universe's deepest questions, including the true nature of dark matter, the wide range of galaxy evolutionary paths, and the incredible diversity in how galaxies form and change over time. As researchers develop sharper tools and gather more data on these elusive structures, UDGs stand as a testament to the universe's endless capacity to surprise, inviting us to rethink the cosmic narrative that has long been taken for granted. Shifting our gaze from galaxies to the profound question of extraterrestrial life, the Fermi Paradox remains one of the most intriguing enigmas of our time. Named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox arises from the clash between the high likelihood that intelligent civilizations exist somewhere in the galaxy and the frustrating absence of any clear evidence or contact with such civilizations. Given the vast number of stars and potentially habitable planets scattered across the Milky Way, it seems almost inevitable that intelligent life should have emerged many times over. Yet despite decades of searching, no definitive sign of alien life has surfaced. Several theories have been proposed to resolve this contradiction. One is the idea that intelligent civilizations are exceptionally rare, with conditions necessary for complex life, such as a large stabilizing moon, a steady climate, and particular geological factors, being extraordinarily uncommon. This perspective, known as the rare Earth hypothesis, suggests that Earth might be a rare jewel in a universe mostly barren of advanced life. Another possibility is that advanced civilizations tend to be short-lived, perhaps falling victim to self-destruction through war, environmental ruin, or catastrophic technological failures before they can communicate across the stars. This grim notion introduces the concept of the Great Filter, a formidable obstacle that blocks the rise or longevity of intelligent life. If humanity has already passed this filter, it might mean we are incredibly fortunate, but if the filter lies ahead, it could portend a bleak future for us all. Alternatively, some suggest the answer may simply be that we haven't looked or listened long enough, or in the right ways. The immensity of space and the limitations of our current technology mean that traces of extraterrestrial civilizations could be out there, hidden from our view. There's also the idea that advanced civilizations might deliberately avoid contact with us or use communication methods so advanced and unfamiliar that we cannot yet recognize them. The Fermi Paradox, in this light, remains a profound challenge that pushes humanity to rethink not only our place in the cosmos, but also how we search for companionship among the stars. Lastly, there are fascinating speculative theories about the very nature of extraterrestrial life that challenge our conventional understanding. These theories suggest that life beyond Earth might not resemble anything we know or expect. Instead, alien civilizations could exist in forms so radically different from ours that they might be virtually impossible for us to detect or even comprehend. This idea pushes us to rethink what it means to be alive, and to consider the possibility that life might thrive in environments or ways far removed from the carbon-based, water-dependent life forms familiar to us. By exploring these possibilities, we not only broaden our search strategies, but also deepen our understanding of our own place in the vast cosmos and the complex forces that shape the emergence and survival of intelligent beings. One of the most enduring puzzles in this field is the Fermi Paradox, the contradiction between the high probability of extraterrestrial civilizations existing somewhere in the universe and the lack of any definitive evidence or contact with such civilizations. This paradox continues to provoke intense debate among scientists, philosophers, and enthusiasts alike. What does it mean for humanity's future in the cosmos if we are truly alone, or if advanced civilizations deliberately avoid detection or exist in ways beyond our grasp? The implications are profound, touching on everything from the destiny of intelligent life to the very nature of consciousness itself. Turning from life to the cosmic backdrop, the cosmic microwave background radiation, commonly known as the CMB, serves as a remarkable relic from the infancy of our universe. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely, leaving behind this faint afterglow that blankets the entire sky. The CMB is astonishingly uniform in temperature, but nestled within this smooth glow lies a mysterious anomaly called the CMB Cold Spot. This region is notably cooler than its surroundings by a tiny fraction, less than 1 part in 100,000, compared to the average temperature of the background radiation. Scientists have proposed several intriguing hypotheses to explain this cold spot. One leading idea is that it marks the presence of a colossal cosmic void, an immense region with far fewer galaxies than expected. Such voids can influence the distribution of matter and energy, potentially causing localized cooling effects in the CMB. Another compelling theory suggests that the cold spot could be an imprint of gravitational waves, ripples in the fabric of space-time, originating from the universe's rapid expansion during cosmic inflation shortly after the Big Bang. These waves might have left subtle marks on the CMB as the radiation traveled across the cosmos, creating the temperature variations we observe today. Despite the allure of these ideas, the true origin of the cold spot remains one of the great mysteries of cosmology. Researchers continue to study detailed observations and refine theoretical models to unlock the secrets hidden in this cosmic wrinkle. Understanding the cold spot not only sheds light on the universe's large-scale structure, but also challenges and enriches our comprehension of cosmic evolution itself. Moving to a grander scale, the ultimate fate of the universe is a question that has captivated humanity for centuries. Cosmologists have proposed several scenarios that could determine how everything unfolds in the far future. One widely accepted possibility is the Big Freeze, also known as the heat death of the universe. In this scenario, as the cosmos expands endlessly, galaxies will drift further apart, stars will burn through their nuclear fuel, and the universe will grow ever colder and darker. Eventually, stars will flicker out, galaxies will fade, and the cosmos will reach a state where no thermodynamic processes occur, an eternal silence where energy is uniformly spread and no work can be done. Alternatively, there is the concept of the Big Crunch. If the density of matter in the universe is sufficient, gravitational attraction could slow and eventually reverse the expansion, pulling everything back into a catastrophic collapse. This would bring the universe back to an unimaginably hot, dense singularity, possibly the precursor to a new cosmic cycle, akin to a phoenix rising from the ashes of its predecessor. A third dramatic possibility is the Big Rip. This theory depends on the mysterious force known as dark energy, which currently drives the accelerated expansion of the universe. Should dark energy grow stronger over time, it could tear apart galaxies, stars, planets, and eventually even atoms themselves, dissolving all cosmic structures in a violent end. Each of these ultimate fates reflects our current understanding of physics and raises profound questions about the nature of existence, time, and reality. As scientists continue to develop advanced observations and sophisticated models, these theories inspire ongoing exploration and a deeper appreciation for the universe's intricate and awe-inspiring complexity. The concept of heat death, or the Big Freeze, is rooted in the second law of thermodynamics, which states that in any isolated system, entropy, or disorder, tends to increase over time. As the universe ages, energy becomes increasingly spread out and less available to do work. Stars will burn out one by one, galaxies will drift apart, and the cosmos will grow cold and dark, eventually reaching a uniform temperature where no energy gradients exist to power any processes. This distant future paints a stark contrast to the vibrant and dynamic universe we inhabit today, reminding us of the fragile and fleeting nature of cosmic life. The universe, in the distant future, will transform into a place stark and desolate, as the stars exhaust their nuclear fuel and gradually cease to shine. What will remain in this vast cosmic wilderness will take on a cool, dim quality, a shadow of the brilliant lights that once illuminated the cosmos. This long, drawn-out era is known as the degenerate era, an age dominated by the remnants of once radiant stars. White dwarfs, neutron stars, and black holes will be the principal actors on this fading stage, slowly cooling and losing their energy over incomprehensibly long timescales. As eons pass, even these remnants will disappear. Black holes themselves, often seen as eternal cosmic vaults, may eventually evaporate through a mysterious quantum process known as Hawking radiation. This phenomenon suggests that black holes lose mass by emitting particles, and over unimaginable periods, this process will leave behind nothing but a thin scattering of elementary particles drifting in an ever-expanding, freezing void. This vision of the universe's heat death confronts us with profound questions about time, existence, and permanence. It is a sobering reminder of the universe's dynamic nature, how everything we see is in constant flux, evolving toward a final fate. Though this future lies so far beyond our present experience, it invites deep reflection on the cycle of cosmic life and the ultimate impermanence of all things. Another gripping hypothesis about the universe's end is the Big Rip, a scenario far more violent and dramatic than the slow dimming of stars. This theory proposes that the universe's expansion, driven by the mysterious force called dark energy, will not just continue but accelerate to such an extent that it tears apart every structure in existence. Unlike other expansion models that slow down or stabilize, the Big Rip envisions a future where dark energy grows increasingly powerful, relentlessly stretching the fabric of space itself. As dark energy's influence swells, it overpowers the gravitational forces that hold galaxies, star systems, and planets together. First, entire galaxies will be ripped apart as their gravitational bonds fail to withstand the growing expansion. Then, star systems will dissolve, followed by planets being torn from their orbits. Ultimately, the forces become so intense that even atoms and subatomic particles are ripped apart, leaving a universe in a state of utter disintegration. Central to this scenario is the equation of state of dark energy, a description of how dark energy behaves and changes as the universe evolves. If the density of dark energy increases over time instead of remaining constant, it would cause the expansion rate to speed up catastrophically. Scientists are actively researching dark energy's properties, hoping to determine whether this haunting fate is a real possibility. Imagining the Big Rip encourages us to ponder the fundamental nature of existence and the forces shaping the cosmos. It reminds us that the universe's destiny remains one of the greatest mysteries, challenging our understanding of time, space, and the limits of reality itself. Though speculative, this vision fuels both scientific inquiry and popular imagination, pushing the boundaries of what we know about the universe. In stark contrast, the Big Crunch offers a very different cosmic finale. Today, we observe galaxies moving away from each other, evidence that the universe is expanding, and doing so at an accelerating pace, thanks to dark energy. The cosmic microwave background radiation and distant galaxy observations have solidified the view that our universe is not only growing larger, but speeding up in its growth. But what if this expansion eventually halts and reverses? The Big Crunch imagines exactly that. Gravity pulling everything back together if the universe's density is high enough to overcome dark energy's push. Instead of drifting apart, matter would begin to coalesce, reversing the universe's expansion and triggering a massive contraction. As this collapse unfolds, galaxies, stars, and planets would merge under the relentless tug of gravity. The universe would become an increasingly hot and dense environment, the opposite of the cooling, expansive cosmos we know today. In the final moments, all matter and energy would converge into a singularity, a point of infinite density, resembling the conditions at the dawn of the Big Bang. This cataclysmic event would mark a complete reversal of the universe's current trajectory, a dramatic pivot from expansion to contraction, from cool vastness to crushing heat and density. The Big Crunch offers a powerful and poetic counterpoint to the universe's mysterious beginning and its uncertain end, reminding us how much remains unknown about the cosmos' ultimate fate. The Big Crunch theory not only brings to light a profound conflict between the immense pull of gravity and the mysterious force known as dark energy, but it also opens up a cosmic window into cyclical models of the universe, models where existence itself may endlessly repeat. Imagine a universe that doesn't just expand once and fade away, but instead breathes through cycles of birth, collapse, and rebirth. This vision shatters the traditional idea of time as a straight line, compelling us to rethink the very fabric of cosmic history and the nature of existence itself. At the heart of this cosmic drama is dark energy, an invisible yet powerful force that dominates about 70% of the universe. First discovered through the observation of distant, exploding stars called supernovae, dark energy behaves in a way that defies our everyday understanding. While gravity works to pull matter together, slowing the expansion of the universe, dark energy pushes the cosmos apart at an ever-increasing pace. This counterintuitive tug of war leads to galaxies racing away from each other faster than ever before, suggesting that dark energy's repulsive influence far outweighs gravity's attraction on grand scales. The future of the universe hinges on how dark energy behaves over time. If it remains steady, the cosmos may drift into a heat death or big freeze, where all stars burn out and space becomes a cold, dark void. On the other hand, if dark energy grows stronger, it could lead to a catastrophic big rip, tearing apart galaxies, stars, planets, and even atoms. Such a fate would mark the ultimate disintegration of everything we know. Scientists around the world are racing to understand dark energy's nature because unlocking its secrets could reveal the universe's ultimate destiny and provide deeper insights into the fundamental forces shaping reality. Technological marvels like the James Webb Space Telescope have revolutionized our ability to peer into these cosmic mysteries. Orbiting far beyond Earth's atmospheric veil, the James Webb can capture detailed images across a range of light wavelengths, especially in the infrared spectrum. This capability is crucial because many regions of space, especially those where stars and galaxies are born, are cloaked in dense dust clouds that block visible light. By seeing in infrared, the telescope can penetrate these cosmic veils, unveiling the hidden processes of star formation and revealing the composition of galaxies billions of light years away. Through these observations, scientists are piecing together the story of how the universe evolved over billions of years, from its earliest moments to the complex cosmic web we observe today. In this unfolding story of the cosmos, the interplay between gravity, dark energy, and cosmic time challenges not only our scientific understanding, but also invites us to reflect on the nature of existence itself, offering a humbling glimpse into a universe that may be far more dynamic and cyclical than we ever imagined. Furthermore, the telescope's cutting-edge design incorporates advanced instruments that dramatically boost its sensitivity and resolution, allowing it to peer deeper into the cosmos than ever before. This remarkable capability enables it to observe light traveling from over 13 billion years ago, capturing snapshots of the universe as it appeared just moments after the Big Bang. By delving into this deep field of vision, the telescope opens a window into the earliest chapters of cosmic history, an era previously shrouded in mystery. Its observations provide critical clues about how galaxies first formed, evolved, and transformed over billions of years, enriching our understanding of the universe's grand narrative. The discoveries emerging from this incredible space observatory are poised to revolutionize how we comprehend the cosmos. By gathering and meticulously analyzing data from a wide array of celestial phenomena, it tackles some of the most profound questions in astronomy. What shapes do stars and galaxies take in different stages of their lives? 1. What exactly constitutes the mysterious dark matter and dark energy that make up most of the universe's mass and energy? And importantly, could there be habitable worlds scattered beyond our own solar system? The insights gained promise to weave a far more detailed and nuanced tapestry of the universe and our place within its vast expanse. Gravitational lenses represent one of the most fascinating natural phenomena in astrophysics. These occur when a massive object, such as a galaxy or a galaxy cluster, lies between a distant light source and an observer on Earth. The gravity of this foreground object warps space-time itself, bending the light traveling from the distant background source in a manner predicted by Einstein's theory of general relativity. This bending can create multiple images, arcs, or even rings of the distant galaxy or star, effectively magnifying and enhancing the visibility of celestial bodies that would otherwise remain too faint to detect. Astronomers have harnessed gravitational lensing as a powerful cosmic tool. By studying the bent and magnified light from these distant galaxies, they can extract invaluable information about their composition, internal structure, and rates of star formation. Remarkably, gravitational lensing can amplify the brightness of these remote objects by several times, making it possible to observe galaxies located billions of light years away. This cosmic magnification pushes the frontiers of astronomical exploration, allowing scientists to peer deeper into space and time than ever before. Moreover, gravitational lenses offer another crucial benefit. They reveal details about the mass of the lensing object itself. By analyzing the specific distortions caused by the lens, researchers can estimate how mass is distributed within the foreground galaxy or cluster. This is particularly important because much of this mass is dark matter, invisible material that does not emit or absorb light, but exerts gravitational influence. Understanding how dark matter is spread throughout these lenses helps scientists unlock secrets about the universe's invisible scaffolding, shedding light on the fundamental makeup of galaxies and cosmic structures. In essence, gravitational lenses serve as natural cosmic magnifying glasses, offering astronomers a unique perspective on the universe's structure and its evolutionary history. As they continue to study these phenomena, researchers gain vital data that deepen our understanding of cosmic formation, the distribution of matter, and the very nature of gravity itself. These insights open new pathways for discovery, greatly expanding our view of the cosmos and its underlying mechanics. Neutrino detectors also play a pivotal role in unraveling cosmic mysteries. Neutrinos are tiny, nearly massless particles produced in enormous quantities during some of the universe's most energetic events. These include violent supernova explosions, the nuclear reactions powering our sun, and the high-energy collisions of cosmic rays with matter. Because neutrinos interact only weakly with other particles, they can travel immense distances through space without being absorbed or deflected. This makes them unique cosmic messengers, capable of revealing details about distant and otherwise hidden energetic phenomena. One of the most groundbreaking applications of neutrino detection lies in studying supernova, the cataclysmic explosions marking the death of massive stars. When a star explodes in a supernova, it unleashes a colossal burst of energy and emits a flood of neutrinos within seconds. Detecting these neutrinos allows scientists to probe the very core of the explosion, offering critical insights into the complex processes that lead to the formation of neutron stars or black holes. This information is vital to understanding how stars evolve and die, as well as how galaxies grow and change over time. By combining the extraordinary capabilities of advanced telescopes, gravitational lensing, and neutrino detectors, humanity is gaining an unprecedented window into the cosmos. These tools together allow us to explore the universe's most profound mysteries, from its earliest moments after the Big Bang to the intricate life cycles of stars and galaxies, shaping a richer, more comprehensive understanding of the vast universe we call home. Moreover, neutrino detectors play a crucial role in advancing our understanding of some of the most energetic and enigmatic phenomena in the cosmos. These detectors do more than just catch elusive neutrinos. They serve as vital tools for investigating high-energy cosmic rays, particles so energetic that they challenge the very limits of known physics. When these cosmic rays collide with atomic nuclei in Earth's atmosphere, they generate a cascade of secondary particles, including neutrinos. By closely monitoring these neutrino interactions deep within subterranean detectors, scientists gain a rare glimpse into the origins of cosmic rays, tracing them back to their powerful and mysterious sources. These potential sources range from active galactic nuclei, where supermassive black holes unleash torrents of energy, to gamma-ray bursts, the universe's most intense explosions, and other extreme astrophysical environments that push the boundaries of nature's forces. Working alongside traditional telescopes and observatories that capture light, gravitational waves, and other particles, neutrino detectors form a critical part of the emerging field of multi-messenger astronomy. This collaborative approach merges diverse signals from across the electromagnetic spectrum and beyond, providing a richer, more detailed picture of cosmic events. Thanks to recent breakthroughs in neutrino detection technologies, scientists have significantly improved their sensitivity and precision in locating the exact sources of these high-energy neutrinos. As researchers venture further into the unexplored realm of neutrino astronomy, the discoveries made hold the promise of unraveling some of the most profound mysteries of the universe, offering insight into the violent processes that sculpt galaxies, drive stellar explosions, and shape the cosmos itself. Interferometry stands as another groundbreaking technique revolutionizing the field of astronomy by vastly enhancing both the resolution and sensitivity of celestial observations. At its core, interferometry harnesses the wave nature of light, allowing astronomers to combine light waves collected from multiple telescopes spaced apart by various distances. This combination produces interference patterns, where light waves can either amplify one another through constructive interference or cancel each other out through destructive interference. By precisely analyzing these interference patterns, scientists can extract extraordinary details about distant astronomical objects, including their brightness, shape, and distance, far surpassing what any single telescope could achieve on its own. In effect, interferometry creates a colossal virtual telescope, opening up new frontiers of observational capability. There are multiple forms of interferometry, each optimized for different wavelengths of light. Radio interferometry, for instance, employs arrays of radio telescopes like the renowned Very Large Array in New Mexico. This method yields astonishingly sharp images that allow researchers to probe the complex structure of faraway galaxies, unravel the dynamics of stars, and investigate phenomena such as cosmic masers, natural microwave lasers in space. On the other hand, optical interferometry merges light gathered by optical telescopes to sharpen visual observations. Projects like the Very Large Telescope Interferometer in Chile showcase how this technique enables astronomers to measure star diameters, study surface features, and even detect exoplanets orbiting distant suns. By combining the strengths of multiple telescopes, interferometry unlocks a treasure trove of information that advances our understanding of cosmology, stellar evolution, and the intricate dance of galaxies. Looking ahead, space-based observatories are poised to revolutionize our view of the universe by escaping the distortions and light pollution of Earth's atmosphere. Placed beyond our planet's protective blanket, these advanced observatories can observe the cosmos in wavelengths that are otherwise blocked or blurred, including ultraviolet, infrared, and X-rays. The James Webb Space Telescope, with its primary focus on infrared light, exemplifies this new era. It allows astronomers to peer deeper into cosmic history than ever before, studying star and galaxy formation from the universe's earliest epochs. Future missions, such as NASA's proposed Habitable Worlds Observatory, aim even higher. directly examining the atmospheres of exoplanets in search of signs that they might support life. By detecting biosignatures or indicators of habitability, these observatories could transform humanity's understanding of life beyond Earth, opening the door to profound questions about our place in the vast cosmos. Together, neutrino detectors, interferometry, and next-generation space observatories represent a convergence of technologies pushing the boundaries of astronomical exploration. They offer a multi-layered approach to deciphering the universe's most violent, energetic, and beautiful phenomena, promising discoveries that will redefine our cosmic perspective for decades to come. Additionally, the future of space-based observatories holds incredible promise for deepening our understanding of the universe, particularly in unraveling the mysteries of dark matter and dark energy. Together, these two enigmatic components make up approximately 95% of the total mass and energy in the cosmos. By employing cutting-edge imaging techniques and conducting vast, large-scale surveys of galaxies across the universe, these next-generation observatories will be equipped to map the distribution and characteristics of dark matter with unprecedented precision. This will significantly inform and refine our theories regarding the universe's structure and its ongoing evolution. Understanding the role of dark energy in the accelerated expansion of the universe remains one of the most profound challenges facing cosmology today. Future observatories equipped with more sensitive instruments and innovative observational strategies will collect vital data to shed light on this cosmic puzzle. Technological advancements will enable these instruments to detect far fainter celestial objects than ever before, allowing astronomers to make measurements with greater accuracy and detail than previously possible. The cumulative data amassed from these missions will create a far more comprehensive picture of the universe's history, whether by mapping the faint afterglow of the Big Bang, known as the cosmic microwave background radiation, or by investigating the birth and formation of the very first stars and galaxies. These ambitious space missions promise to push our horizons wider, letting us peer deeper into the universe's most profound mysteries. They will help us not only refine the existing cosmological models, but also develop entirely new theories that challenge our current perceptions, reshaping how we understand our place in the vast cosmic landscape. Parallel to this, there is growing interest in alternative approaches to explaining the behavior of gravity on cosmic scales, particularly through the lens of modified gravity theories. These propose fundamental changes to our understanding of gravitational interactions without relying exclusively on dark matter. Classical physics, governed by Newton's law of universal gravitation and Einstein's theory of general relativity, has long served as the foundation for understanding gravity. However, observations of galaxies and galaxy clusters have consistently revealed anomalies that challenge these traditional theories. For example, stars in the outer regions of galaxies orbit their centers at speeds far higher than what Newtonian physics would predict. According to classical mechanics, stars farther from the galaxy's core should move more slowly due to the weaker gravitational pull from visible matter. Instead, these stars maintain unexpectedly high velocities, suggesting the presence of an unseen mass, dark matter, that provides the necessary gravitational force. Modified gravity theories, such as modified Newtonian dynamics, MOND, offer an alternative explanation. They suggest that gravity might behave differently under the low accelerations found at the outskirts of galaxies. Instead of attributing the star's rapid motions to invisible matter, these theories propose that the laws governing gravity themselves change under such conditions. This provocative idea challenges the long-standing belief in dark matter by suggesting that the gravitational effects attributed to this mysterious substance might instead emerge from new properties of gravity itself. This shift in perspective not only provides alternative explanations for galaxy dynamics, but also raises profound questions about the nature of space, time, and gravity on a grand cosmological scale. If gravity behaves differently than we currently understand, it could have significant implications for the formation and evolution of cosmic structures, potentially altering our models of the universe. However, while modified gravity theories show intriguing potential, they face challenges in accounting for certain cosmological observations that dark matter models explain more seamlessly, such as the fluctuations in the cosmic microwave background and the large-scale structure of the universe. This ongoing debate represents one of the frontiers of modern astrophysics as researchers continue to gather data and refine their models. The question remains open. Does dark matter exist as a form of invisible mass? Is gravity itself fundamentally different from our current theories? Or is there a combination of both at play? Each new observation pushes the boundary of our knowledge and opens the door to new possibilities in understanding the cosmos. At the cutting edge of theoretical physics, loop quantum gravity represents a bold effort to unify the seemingly incompatible realms of quantum mechanics and general relativity. General relativity brilliantly describes gravity on large scales, showing how massive objects warp the fabric of space and time. Quantum mechanics, on the other hand, governs the behavior of particles and forces at the tiniest subatomic level. Yet, when these two frameworks meet, such as in the extreme environments of black holes or the very early universe, they produce conflicting predictions. Loop quantum gravity offers a radical reconceptualization of space and time. It suggests that rather than being a smooth, continuous fabric, space-time is composed of discrete, quantized units, tiny, loop-like structures known as spin networks. These networks represent the fundamental quantum states of the gravitational field, essentially weaving the fabric of reality from the smallest building blocks. Imagine space-time as a digital image made of pixels rather than a seamless canvas. This granularity is central to loop quantum gravity's approach. One of the most significant achievements of this theory is its potential to resolve singularities, the infinitely dense points predicted by classical general relativity to exist at the centers of black holes or at the moment of the Big Bang. By applying quantum principles, loop quantum gravity predicts that quantities like area and volume come in discrete chunks, preventing the formation of true singularities. This means that at extremely small scales, space-time behaves differently, avoiding the mathematical infinities that have long troubled physicists. Through these groundbreaking ideas, loop quantum gravity pushes the boundaries of our understanding, offering a glimpse into the very fabric of reality and the fundamental nature of gravity itself. It represents a promising path toward a unified theory of physics that can describe the universe in its entirety, from the cosmic vastness to the quantum realm. Moreover, loop quantum gravity offers a groundbreaking approach to understanding the fabric of the universe by emphasizing a background-independent formulation. Unlike many other attempts to unify quantum mechanics and gravity, this theory does not assume a fixed space-time backdrop. Instead, it treats spacetime itself as a dynamic entity, evolving and changing, much like how general relativity views gravity not as a force, but as the curvature of spacetime caused by mass and energy. This shift away from a rigid background is crucial because it aligns loop quantum gravity more closely with the principles of general relativity, creating a framework where the geometry of spacetime is not static, but fluid and emergent. As scientists delve deeper into the mathematical structures underpinning loop quantum gravity, they rely heavily on advanced computational techniques and abstract mathematical formulations. Although the theory remains in its early stages, its promise lies in its potential to finally bridge the century-old gap between quantum mechanics, the physics of the very small, and general relativity, which governs the cosmos on the largest scales. If successful, loop quantum gravity could revolutionize our understanding of the universe by providing a coherent picture of how the microscopic quantum world and the macroscopic gravitational cosmos interact seamlessly. This unified vision could unlock answers to long-standing puzzles, such as the nature of black holes, the origin of the Big Bang, and the fundamental structure of spacetime itself. Closely related to these profound questions is the holographic principle, an intriguing and provocative concept emerging from the intersection of black hole physics and string theory. The holographic principle suggests that our seemingly three-dimensional universe may actually be a projection encoded on a distant two-dimensional surface, much like the way a hologram stores a three-dimensional image on a flat film. This revolutionary idea arose from the study of black holes and their thermodynamics, where pioneering physicists such as Jacob Bekenstein and Stephen Hawking made a startling discovery. They found that the entropy of a black hole, an indicator of its internal disorder or information content, is proportional not to its volume, as one might expect, but to the surface area of its event horizon, the boundary beyond which nothing can escape. This insight turned conventional wisdom on its head, suggesting that the information contained inside a black hole does not reside within its interior space, but is somehow encoded on its surface. Extrapolating from this, the holographic principle posits that the entire universe might work the same way. All the information that describes the cosmos could be encoded on a vast two-dimensional boundary. If this is true, it has far-reaching implications for our understanding of space, time, and gravity. It challenges the traditional idea of locality, the assumption that objects are only influenced by their immediate surroundings, by proposing that at the most fundamental level, all points in space may be interconnected through the information imprinted on these boundary surfaces. Such a perspective could open new pathways for tackling some of the most elusive problems in physics, particularly how gravity behaves near the quantum scale, where the smooth fabric of space-time predicted by general relativity breaks down. By blending concepts from quantum mechanics, geometry, and information theory, the holographic principle provides a fresh lens through which to view the deep interplay between information, space, and gravitational forces. As research continues to advance, these ideas may hold the key to finally reconciling gravity with quantum mechanics, unlocking a more profound understanding of the universe's fundamental laws and the true nature of reality itself. Furthermore, the holographic principle offers a profound window into some of the most perplexing mysteries of modern cosmology: dark energy and dark matter. These two enigmatic components together constitute the vast majority of the universe's content, yet they have stubbornly eluded direct detection or clear understanding. At its core, the holographic principle suggests that the universe's fundamental information is encoded not in the three-dimensional space we perceive, but rather on a two-dimensional boundary, much like a hologram projects a three-dimensional image from a flat surface. This radical idea opens up new avenues for scientists seeking to decode the universe's hidden structure. By exploring how information is stored and processed within a holographic framework, researchers hope to uncover novel theoretical models that bridge gaps between currently disconnected areas of physics. Such frameworks might finally offer explanations for the strange behavior and properties of dark energy, the mysterious force accelerating cosmic expansion, and dark matter, the invisible mass shaping galaxies through gravity. While the holographic principle remains highly theoretical, its implications are far-reaching, challenging our everyday intuition about what reality truly is. It pushes us to reconsider the very nature of existence, suggesting that what we experience as space, time, and matter might be emergent phenomena arising from deeper, more intricate informational patterns. Turning to string theory, the landscape of fundamental physics shifts yet again, proposing a revolutionary view of the universe's building blocks. Instead of point-like particles, tiny dots with no internal structure, string theory posits that the basic constituents of reality are one-dimensional strings that vibrate at different frequencies. This conceptual leap arose from a pressing need to unify the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces, which govern everything from the fall of an apple to the fusion of stars, have long resisted integration into a single, coherent framework, especially when quantum effects come into play. In string theory, the diverse particles we observe, each with unique masses and charges, are manifestations of different vibrational patterns of these fundamental strings. Imagine a guitar string. Pluck it one way and you hear a high note. Pluck it another and a deep tone resonates. Similarly, each mode of string vibration corresponds to a distinct particle, making string theory a promising candidate for a theory of everything that could seamlessly unite all matter and forces. But the theory's boldness doesn't stop there. It predicts the existence of additional spatial dimensions beyond the familiar three dimensions of space and one dimension of time. In its simplest formulations, string theory requires as many as 10 or even 11 dimensions. These extra dimensions aren't simply theoretical decorations. They are crucial for the mathematical consistency of the theory. They are thought to be compactified or curled up so tightly that they remain invisible at the scales we experience daily. Yet these hidden dimensions might govern fundamental physical phenomena, influencing particle interactions and the fabric of reality itself. Another fascinating feature of string theory is supersymmetry, a proposed symmetry linking every known particle to a yet undiscovered partner particle with differing spin properties. Although experiments have yet to confirm supersymmetry directly, this concept could resolve key puzzles in physics, including the hierarchy problem, why gravity is so much weaker than other forces, and the elusive nature of dark matter, which might be composed of these supersymmetric partner particles. As string theory continues to evolve, it propels scientists deeper into questions about cosmology, particle physics, and quantum gravity, promising a transformative understanding of the universe's fundamental workings. Meanwhile, cosmic inflation offers a compelling explanation for a critical epoch in the universe's infancy, a period marked by extraordinarily rapid expansion within an infinitesimally brief moment after the Big Bang. This theory, proposed by physicist Alan Guth and others in the early 1980s, posits that the universe underwent exponential growth, expanding faster than the speed of light over a minuscule fraction of a second. Such an explosive expansion can account for several puzzling features of the cosmos, especially the remarkable uniformity observed on large scales. The universe appears strikingly homogeneous and isotropic, meaning galaxies and cosmic structures are spread evenly in every direction. Yet according to classical Big Bang models, regions of space should have been too far apart to ever interact or share information due to the finite speed of light. Inflation elegantly solves this by suggesting that all these regions were once compacted closely together, sharing the same conditions of heat and density before being violently stretched apart. This rapid stretching smoothed out any initial irregularities, creating the consistent cosmic backdrop we observe today. In this way, the holographic principle, string theory, and cosmic inflation each offer extraordinary insights into the cosmos, challenging our deepest assumptions and expanding the frontiers of human knowledge. Together, they weave a tapestry of ideas that may one day unravel the grandest mysteries of existence, revealing a universe far richer and more complex than previously imagined. Moreover, cosmic inflation presents a groundbreaking explanation for how the universe as we know it came to be. In the briefest fraction of a second after the Big Bang, the universe underwent an extraordinary and rapid expansion, so swift and immense that tiny quantum fluctuations, normally confined to unimaginably small scales, were stretched across vast cosmic distances. These minute irregularities, born from the unpredictable dance of quantum particles, became the very seeds from which all the large-scale structures in the universe eventually grew. Galaxies, clusters of galaxies, and the intricate web of matter spanning the cosmos owe their origins to these primordial ripples. As the universe continued its steady expansion, these initial variations, so slight and subtle, were pulled together by the relentless force of gravity. Over billions of years, this process transformed the universe's early, nearly uniform soup into the complex and breathtakingly diverse cosmic landscape we observe today. From the sprawling spiral arms of galaxies to the dense clusters that bind them, the intricate architecture of the cosmos traces back to this early stage of inflation. Beyond explaining the formation of structure, cosmic inflation also sheds light on one of the universe's most puzzling features: the remarkable uniformity of the cosmic microwave background radiation, or CMB. This faint glow, a relic of the universe's fiery infancy, blankets the sky almost perfectly evenly. Yet within this uniformity lie tiny temperature fluctuations, imperfections that, despite their subtlety, were crucial for the eventual clumping of matter into galaxies. Inflation theory elegantly reconciles these observations, accounting both for the overwhelming uniformity of the CMB and for the small variations that sparked cosmic structure. Today, cosmic inflation remains at the forefront of astrophysical research, captivating scientists who seek to probe its predictions with ever greater precision. Experiments and observations continue to refine our understanding of this pivotal epoch, aiming to unlock deeper secrets about the early universe. By providing a unifying framework to explain fundamental cosmic properties, such as the distribution of matter, the smoothness of the cosmic microwave background, and the very shape and fate of the universe, inflation enriches our grasp of cosmic evolution. It also pushes us closer to unraveling the underlying laws that govern existence itself, offering a profound glimpse into the mysterious forces that shaped everything, from the tiniest quantum fluctuations to the vast galaxies scattered across the night sky.